Are we live? Looks like we're live. Hello everyone and welcome to yet another recreational programming session with Azuzin. How about that? I bet you didn't expect that shit to happen as usual. Let's make a little bit of an announcement and officially start this stream. Hello everyone. I can see people in the chat. Welcome. Let's do the usual thing. A red circle. Live on Twitch. And what are we doing today on Twitch .television website? Today we're implementing a shapes classifier. Right, so I'm gonna give the link to twitch.tv/talking where we're doing all that, and I'm gonna ping everyone who's interested in being pinged, and there we go, the stream has officially started. Right, so today we're going to continue working on deep learning framework in C, right? So nn.h, you can find this thing in here. I'm going to copy paste it in the chat. And right, I'm going to, for people who's watching on YouTube, I'm going to actually put it here in the description. Right, so we've been developing this framework for quite some time. All right, the things that we developed are rather interesting, right? So I think we did a little bit of a circuitry, all right? We implemented an adder, which is quite cool. I'm really proud of this adder. It actually learns super fast. Right, we also did image interpolation, right? A thing that is rarely done. So usually people, I think only recently, like a real paper about using latent space of neural networks for storing images was released at some point. I don't really remember, but somebody in the Discord chat actually posted, you know, a link to a paper that explored the same idea that we explored on the stream, and they claimed that nobody has ever done that before, something like that. It was actually quite funny, I think. But I mean, I think they claimed nobody made a scientific paper on that before, right? So they didn't say that nobody done that before, but they said nobody published a scientific paper. So the thing is, using the latent space of neural network to store images is actually such an obvious idea that I don't think anybody thought that it's worth even like making a scientific paper about that. That's why I think there was no any papers, like serious papers on all of that. But yeah, it's actually a pretty straightforward idea, right? So, and it's so obvious and straightforward that even such a dummy as myself came up with that idea, right? So that's probably why nobody posted that. Nobody posted a paper about this kind of stuff. So we did these kind of things, but we didn't do the classics, the all-time classics of neural networks, which is an image classifier. We never actually implemented an image classifier. The reason why I never implemented image classifier, because it's kind of like, you know, how to say that? Like everyone does that. Like everyone who learns neural network, the first thing they're gonna do, they're gonna just grab NIST database and just implement an image classifier. It's just like, it's fucking boring. So that's why I kind of postpone all of that. But I think the time has come to finally do that. So we're not going to be doing a NIST database. What we're going to do, we're going to try to generate the data on which we're going to be training neural network ourselves. Right. So that way we don't have to worry about like a clean data or anything like that. And that will actually allow us to test different aspects of neural networks learning how to classify images. Right. So we're going to have a lot of control over our database, and we'll be able to maybe change some features and see how that changes the behavior of the learning process. I think that's going to be useful. So the idea that I want you to implement today, it comes actually from one of the previous stream, right? So Perceptron, I think that's what it's called. But the idea was to implement the first ever Perceptron. Yeah, there we go. So I wonder if there is a link to the VOD for the, yeah, there is a link to the VOD. Right, so, and the idea is actually super simple. Right, so you sort of like have a screen that perceives an image. Right, and as far as I know, each individual cell in here is sort of a weight. And essentially you just sum up all of the things, and if it comes out as like 0, you basically assume that it's a circle, if 1 is a rectangle. But I don't remember the specific, I don't remember how you classify it because it was some time ago. Right, but essentially it was not like a really classical neural network, and the training process was actually kind of dumb, and it didn't yield very interesting result. But what I liked about it is that you can generate the data yourself. right? You can generate the data yourself. You can just generate a bunch of rectangles. You can generate a bunch of circles and just train a neural network on that, right? So you can train a neural network on that. So you can find this thing in here. There will be some links to like the link to the video in here. So I really recommend to watch it. I think it turned out quite kind of interesting. So I'm gonna also put this thing in the description. Right. So let's go ahead and just start implementing the demo, right? Let's actually start implementing the demo. So I'm going to create something like shape.c and let's actually include this kind of thing. Right, so this is going to be that, printf, hello world. And let's add this entire stuff to the build process, right? So we're not going to build everything, we're only going to build the shape, right? Let's only build the shape. There we go. So let's take a look at how much time it was actually almost instant. Why is it so fast? This is probably because we don't include STB libraries, right? Because if you just include something like STB image write, which we probably will need, right, to just like debug whatever we generated, it actually takes enormous amount of time, though this is probably because we didn't include the implementation, right? So we do STB image write implementation, right, implementation. I think it will, yeah, now we're fucking talking. Now we're talking. So I can even time this entire thing. Look at that. Look at that, it took 2.5 seconds, but if we don't include the implementation of this library, it's just like 100 milliseconds, 150 milliseconds, right? So that's the difference between including the dependency and not including the dependencies, right? So third-party dependencies are free, literally free. They do not impact your workflow as a developer at all. Completely, they're free. You can just stack them as much as you want. So essentially, what we're gonna do, we're gonna classify small images, right? I wanna actually work on images 28 by 28 because that's the size of the image used by MNIST database, right? So I kind of wanna you know, accommodate to the size of these images, right? Because we're probably gonna use MNIST database in the future episodes, right? So we're probably gonna implement, you know, digit classifier at some point, right? So, and let's just go ahead and define a couple of constants in here, right? So the width is gonna be 28 and height is going to be 28. Maybe I'm gonna say that height is gonna be the same as width, which will make it a little bit easier for me to just change the you know, the resolution or to make it smaller or make it bigger or something like that, but preserve the squareness of this entire thing, right? So, but we're gonna use 28 for now. We're gonna use 28. So for generated images, I think it would make sense to use Olivet. So what do you guys think, right? So the library that we developed quite some time ago, right? So it's kind of interesting how from time to time I have crossovers with like small libraries that I implement. Sometimes I implement them and I think like they're useless, but then it's just like it occurs to me, oh, I could just like use this library I developed like a year ago for this specific case. So you can find it in here. It's all coming together, right? Just like Billy Harrington. It's fucking coming together, right? So here it is. And do I have it downloaded? I didn't think I have it downloaded. I have a folder with third party. Yeah, I don't have it downloaded. So let's actually take it raw. Where is it? Where is the raw? There it is. Okay, so I'm gonna just like download it like that. Even though GitHub implemented the download button, I don't really use it because I still have reflexes to just click on a row, right, click on a row and download with wget. And the reason why I like this workflow a little bit better is because I can control where exactly I can download things, right? Because if I click download, it will always download in the download folder and it's just like, I kind of feel a little bit better if I can just like say download it there or download it there, and I kind of got used to this workflow, so this button doesn't really do anything for me, unfortunately, even though it's kind of cool that they finally came around to implement that button. So it's very cool that such a huge corporation is still capable of implementing download buttons. It's fucking amazing. Anyways, so here's the Olivet. And let's just include the Olivets, I suppose. Right. What else can you do with the library? You can only include it. Olivets, and let's define. It's also STB style. That means you have to do implementation, right? And so what I want to do in here, right? So I probably want to allocate some region into which I'm going to be generating thing, right? So we're going to be having a temporary region for machine learning anyway, right? So because we recently implemented in nn.h a temporary allocator, actually arena allocator. So now the library is allowed to do a lot of intermediate allocations, and all of them should happen within arena allocator, so that then later you can actually deallocate everything at once. It just makes it everything a little bit easier and a little bit more natural, right? We don't have a garbage collector, but we sort of like simulate garbage collector with arena allocators, and it works relatively well, I think. Since we're going to be having this arena allocator for temporary things anyway, we might as well allocate it right away, right? So let's actually do something like region. Let's first allocate the allocator. So how much memory do we want to allocate? So I think 256 megabytes is going to be enough for everyone. 256 megabytes ought to be enough for everyone. And let's allocate some stuff in there, right? So maybe I'm going to do Olivet's canvas. All right, so this is the canvas. I'm going to zero initialize this entire thing, and let's just allocate some pixels, right? So let's allocate some pixels. This is going to be region alloc, and within the temporary allocator, I'm going to allocate width by height pixels, and I need to know the size of the pixel. So size of the pixel is actually OC pixels. Right, there we go. So then I need to set the width and height of this canvas. All right, so this is going to be width. This is going to be height. And you also need to specify the stride, right? Stride is how many pixels you need to skip to get to the next row, right? So that's how basically it works. So essentially it allows you to take sub-images if you want to, right? We're not going to use sub-images, but I mean, the library requires you to have a stride anyway. Otherwise it won't be able to get to the next row. So the next thing we want to do, we probably want to clean up the canvas, Olivet's fill. I'm going to just fill it up with black color, I think. So this is basically black color. And I think I forgot 10. And let's draw a circle, right? Let's draw a circle, like a single circle in here. So this is going to be a circle. OC, we're going to draw it at the center, right? Width divided by 2, height divided by 2, and we have to specify the radius. So let's say that the radius is going to be maybe third of the width, and then we can specify the color, right? So you can't see really shite in this mist, so let me put something behind the screen super quick, so I cannot see shit, the same shit you can see. So then I intuitively try to adjust everything. Right, so we're going to be using, like, I think white color. I want to use strictly black and white colors because it will then it will make it easier to translate them to 0 and 1 for neural networks, right? So because we're going to be taking the entire image, we're going to be feeding it into the neural network, right? So, and essentially the way we're going to approach that, right? So we're going to approach that in a very straightforward way. So just a quick footnote. Yes, I am aware of convolutional neural networks. Yes, we're going to implement them at some point. Yes, this is going to be a separate stream, probably several streams. On one of the streams, we're first going to familiarize ourselves with convolutions in general, and then we will see how to use them in neural network. Don't tell me about convolutional neural network, please. I know about them, right? We're trying to learn things. We're trying to discover things ourselves. Again, so as I already say, it's pointless to run fast if you don't know the direction. I know that you need to use convolutional neural networks because they perform better, right? But there's no point at running fast if you don't know the direction. Yes, I know. Thank you very much. Anyways. So imagine that you have an image, right? So imagine that you have an image. So it consists of like several pixels and stuff like that, right? So let's imagine that this is pixels, and they sort of continue downwards because I'm too lazy to render all of the pixels. Imagine that the pixels like continue there. So and essentially we're gonna have a fully connected neural network, not a convolutional one. I know about convolutional neural networks. I know that they perform better. We're using fully connected because we're trying to learn and discover things. Okay, thank you very much. But that isn't actually, yeah, I know. So, and essentially we can take all of the pixels and we can straighten them up, and we're gonna be basically feeding them into each neuron of the input layer, like so. Right, and then we're gonna have probably a bunch of hidden layers, right? So we're gonna have a bunch of hidden layers that also interconnect here. And then on the output, we're probably gonna have a vector of two things, right? So since we're going to be actually trying to distinguish between circles and rectangles, right? So the first neuron is going to correspond to circle, right? So this is going to be circle. And the second one is going to correspond to rectangle. So this is probably how we're going to approach this entire thing. So first we need to generate the image, and then we're going to be feeding that image into like the first, the input layer, but we're going to be straightening this entire thing up. All right, so, okay, so we just generated a circle, and it would be nice to kind of see what kind of image we generated. So let's actually save it. We already included STB image, right? So let's go ahead and do that. So how do you even use STB image, right? I don't quite remember. So I think it's, yeah, I think it's something like this. So we have to provide the file path. So let's define this variable, file path. Then the output PNG. PNG file path. Width is actually width. Height is that. The amount of components, we have 4 amount of components. We assume RGBA 32, right? So let's actually put 4 in here. So this is supposed to be pixels, and this is stride, right? And we do know stride, but we actually store, the library stores stride in pixels, but we need it in bytes, which means that we need to multiply this entire thing by the size of the pixel, right? So on this thing, if I remember correctly, returns true on success and false on failure, right? If this thing has failed, we probably want to just do something like printf std error could not generate as, and that as is going to be the file path. And then we're going to just exit with non-zero exit code to indicate to the parent program that something bad has happened. Otherwise, we're going to print something like generated output as, right? So because output PNG is this thing. Okay, so that is very cool. Let's go ahead and just print this entire thing. So what do we have in here? We just put some garbage in here, nothing particular special. Region allocator, right? So region comes from the neural network framework, right? So we have to include nn.h, and then we have to define nn implementation. There we go. Is it going to build? It is building actually, so which is kind of cool. And let's try to run shape, and it generated output PNG. Right, let's take a look at this thing. Let's take a look at this thing. Here's the circle, right? Isn't it cool? I think it's pretty freaking cool. So this is the circle that we generated. It even has anti-aliasing, right? So as you can see, it's a very smooth circle, but it's 28 by 28. So we can do this kind of stuff. We can probably even open it in Thech, so we can refresh as we generate more circles and stuff like that. So this is going to be black. Keep zoom VP, and let's go. So I'm going to just zoom in, and that's what we have in here. It's kind of difficult to see the background, but I wonder if I can say that the background has to be gray. Is that something I can say? Can you do gray? That's good. Look at that. Thech is actually a useful program, right? So I don't want it to be super bright, right? Because I don't want to flashbang you, but something like a little bit darker. Even that gray is a little bit bright, in my opinion. It's a little bit too bright. Is there something like a dark gray, if you know what I'm talking about, like a dark gray? No, there is no such thing as dark gray. It literally looks like a gray. It's dark underscore gray, right? Are you debating me, or you literally know know that. Oh, you don't know that because it's literally black. So so somebody said dark gray, but they're literally confabulating things like ChatGPT. So people sometimes ask, why ChatGPT lying and hallucinating? But I mean, it's mimicking people. Like, people do that all the time. It's just like, yeah. They trying to solve the problem and they start hallucinating random shit, like just trying to solve the problem. It's just like, you don't know whether it's underscore or not. Like, you just hallucinated that. And that's basically what ChatGPT doing as well. Right? So just get, yeah, let's use a more like appropriate word, guessed it. We didn't hallucinate that. We guessed it. Right? So we're not hallucinating, we guessed it. If it's ChatGPT, it's hallucinating that. Humans never hallucinate, they're guessing. Right? They're brainstorming. It's not hallucination, it's brainstorming. Okay, anyway. Let's continue. Let's try this kind of thing. So this is going to be just gray. And I want to zoom it in. Can I zoom it in? Thank you very much. It's not even centered properly. Disgusting. This is because it's not odd. It's even, right? So it's not odd, it's even. So what we want to do, we want to actually generate a random circles, right? We want to generate random circles. We can do that, but I don't like the fact that the circles are going to be actually sort of like outside of the area, right? So I think we need to tackle that somehow. One of the things, one of the techniques I like to use for like generating circles that are always within the area is basically generate 2 points within the canvas, and these 2 points will form the rectangle, and then you draw the circle within that rectangle. Since the rectangle ends up being always within the canvas, the circle always going to be within the canvas as well, right? So that's actually kind of a cool technique that I came up with recently, relatively recently, and I'm surprised that that's very simple, right? So essentially, let's give it a try. Let's just generate a couple of points, right? So let's generate x1, and it's gonna be a random point from 0 to width, right? And then we're gonna do y1, which is gonna be from 0 to height. So that's what we have in here, width and height. And we can even just put a pixel in there, right? So we can do Olivet's pixel OC x1 y1, and we can put a red in there. So this is going to be red. So, and y, so this is the first pixel. And let's rebuild this entire thing. And run this entire stuff. And as you can see, we refresh it, and here is 1 pixel. So let's generate the second one. Let's generate the second pixel. And let's also put it on this screen. Let's put it on the canvas. Alrighty, and let's run it. So I have to actually run it. Did I already run it? No, I didn't run it. There we go. So that generated 2 of them, and this particular configuration of pixels kind of sucks, right? Kind of sucks because it doesn't really form a proper rectangle. In fact, I kind of hate it. So let's actually do the following thing, where we're going to be setting the seed every time we run it, actually each second, right? So, and that will generate a random thing every time. Maybe we can set up like a fixed seed, right? I just want to find the seed where it generates 2 points that like make sense at least, right? Because this is kind of bullshit in my opinion. Right, so what do we have in here? That's a little bit better already. So right, so we got 2 points, right, and now we want to try to form a rectangle out of them, right? So let's actually form a rectangle out of them. As far as I know, in Olivet's we have something like frame, right? So we can actually draw a frame, but it accepts a rectangle in the form of a left top corner and width and height. Right, we have this entire thing in a form of 2 points, right? It's not particularly useful. I want x1, y1 to be left top point and x2, y2 right bottom point. So to achieve that, we probably want to actually do the following thing. So if like there is an invariant that x1 is always less or equal than x2, but it can be broken because the points are random. So what we want to do, if x1 is greater than x2, we have to fix that invariant, right? So we want to swap this entire thing, x1 and x2. Right, we're going to be swapping this entire thing, and I'm going to replace x1 like so. After that, we might want to do the following thing, demos shape. So now it's always like in this configuration where it always has a left top corner and bottom right corner. Like it always gonna have that regardless of the seed, because we always fix if it's not true, right? We always fix that if it's not true. So after that, it's quite easy to find out the width of this entire thing is just x2 minus x1, and height is, you know, y2 minus y1. So, and we can just go ahead and render the rectangle that we formed out of this entire thing. So x1, y1, width and height. The thickness is going to be actually 1, and let's use the color red, right? So we don't need this entire thing. Okay, and this is the random rectangle that we've got. If we use a random seed every time, it's always going to be a rectangle that is within, right? Sometimes it's going to be derpy like that, but it's always going to be within the canvas, right? So this thing is always going to be within the canvas. We keep regenerating this thing, but no matter how many times we regenerate this entire thing, it's always going to be within the canvas, which is actually rather useful, in my opinion. Right. So what that means if you render a circle within that rectangle, it's always going to be within the canvas. So, and we can use the same technique to generate random rectangles as well, right? Instead of rendering the circle, just fill it up, fill the whole thing up. Right, and so it's basically the same algorithm. The only problem is that sometimes it get like this kind of shit is just like, it's not particularly useful. It would be nice if we like had a minimum width and height, right? A minimum width and height. So how can we achieve that? Well, it's kind of difficult to achieve that. We can just repeat that, right? So essentially we can try this thing one time, right? We can try this thing one time, and if width and height turned out to be like less than 4, right? For instance, here we have it, actually this is 3. Right, this is more of a 3 because 0, 1, 2. I think frame takes into account, so this is actually 3. Right, so if it's less than 4, just try again, right? So it would be kind of nice if we could do something like if width is less than 4 or height is less than 4, then go to again, and we can put again in here. But here is an interesting thing. We already have loop constructions that can do this kind of stuff, don't we? We already have this kind of loop construction. It's a do while. This is one of the rare moments when you probably want to use do while. People shit on loops with post conditions all the time, but they have their legitimate actually use case. And their very often legitimate use cases is when you want to try one operation, and if that one operation didn't really work out, you want to try again, right? So do while or loops with post conditions are really useful for retrying things, right? So they're very useful for retrying things. Because you want to try thing at least one time, and if it failed, you want to try to do this thing another time, and so on and so forth. And this is like a legitimate use case for this entire thing, right? And but these days, loops with post conditions are not really used that very often, right? So they exist in C-style languages, nobody uses them. In Python, they're completely non-existent, right? So because you can replace them with just like while loops, you can just try one thing and like do the rest of them in a while loop. But yeah, so one of the problem here is that we kind of need to put the declaration of these variables outside of the loop, right? Because this does not really try this thing again. So these variables are not going to be visible outside of the loop, right? So what we have to do is probably just declare all this stuff outside, so it all becomes visible. H, do we have anything else? I think that's totally fine. So, and in here, we're going to literally just try this entire thing. So, and yeah, now if I try to rebuild this entire thing, oh, there we go. So, and now, no matter how many times we generate this entire thing, it's never going to be this scuffed. It's never going to be small, right? It's always like at least 4, which is precisely what we want, right? So it fixed this entire thing. But you have to be like a little bit careful, because it is possible to come up with such width and height, right? And we're probably going to be modifying width and height to adjust different things. It's very easy to come up with width and height that will make this loop infinite, right? You will never come up with a combination of x1, y1, x2, y2 that actually fits that specific criteria. So one of the things we probably want to do is to try this thing a limited amount of times. So essentially, and I++ less than 100, right? So we can try that at least 100 times, right? We can try this at least 100 times. And yeah, after that, we probably want to assert something like this. Right, all right, so let's actually assert that w is greater or equal than 4, and this thing greater or equal than 4. So essentially, that will ensure that the program will crash if we exceeded all of the 100 attempts, which will indicate to us that maybe we have to pick a different width and height, right? So maybe we have to indicate a different width and height. So, all right, so that's the easiest way to approach this kind of thing. You can approach that differently, right? So I think that's the easiest to think about it. Just like try again, whatever, like it doesn't matter. Just try again. Okay, cool. And how can we now generate a circle within this entire thing? Right, we can't really fill in the circle, right? Because the circle is like squarish, you know what I mean? The boundary box of the circle is square, right? So that means to render a circle within a rectangle, we have to take a square and kind of fit it within the rectangle, right? So essentially, if width is less than height, right? If width is less than height, that means it's sort of like a vertical thing. Let me actually rerun this thing a couple of times so we can see. Yeah, there we go. So if width is less than height, that means the circle is going to be somewhere here, right? So it's going to be like somewhere here in the middle. So that means in terms of the center, right? So we need to basically pick a radius. Radius is going to be essentially width, right? Width divided by 2. Yeah, I see. So essentially the radius is going to be the minimum between width and height. If width is less than height, that means it's going to be width, otherwise it's going to be height, and this is half of this entire thing, right? So that's the radius of the circle. But in terms of where it is going to be located, it is going to be located at the center, which is x1 plus w divided by 2, y1 plus h divided by 2. And the radius is basically this entire thing, and that will actually put this entire thing right in the center of the rectangle, right? So let's go. Let me try to just run this entire thing. So that didn't really work. So I think I need to include time because it keeps throwing a warning for this entire thing. And let's put the red color. Let's put the red color. I should probably have a predefined colors in olivec, just like, you know, how is it called, raylib, right? Because raylib has predefined colors. There we go. So this is the circle within the rectangle, right? It goes a little bit outside because of the anti-aliasing, but I mean, hey, that works. And by the way, I think circle, I want you to make it like actually white. Right, so let's actually make it white. There we go. Doesn't it look cool? Doesn't it look cool? I think it looks pretty cool. So let's actually keep generating different things, right? So here are random circles that are always within this entire thing. right? They all go a little bit outside, and I wonder if this is because of the anti-aliasing. We can turn off the anti-aliasing. This is one of the things we can do. In third-party Olivets, right, we have a AA resolution, yeah. So it's set to 2. It's basically how many like subsamples do we have, right? So we can set the amount of subsamples to be 1, right? And that means that effectively turns off the anti-aliasing. Right? Effectively. Now, if I try to rerun this entire thing, looks like a flag. Like, yeah, people say that it looks like a flag. Every time I work with Olivets or do some different things, people say that it looks like a flag. Probably because, no, it's not about this thing. Huh, that's very interesting. But I mean, that's fine, right? So if one pixel is gonna go outside of the boundaries, I don't think it's gonna create that much problem. Right, and now we can just turn off the frame. Let's just turn off the frame, and we're good to go, right? I'm not sure if this is the most optimal way of generating the circles of the required properties, right? So I'm pretty sure it is not, but it kind of works, right? It kind of works. So this is a bunch of these things. Okay, so that's pretty cool. So we can now keep generating random circles. In fact, we can now try generate random rectangles. So essentially, we already have all of the information to generate a rectangle. Just fill rect, which starts at x1, y1 with width and height, and there we go. You're generating random rectangles. It's that simple, actually. So it doesn't use R, it doesn't use radius because, I mean, it's not a circle, but it's going to work. There we go. There they are. So isn't it cool? And we can generate thousands of these things, right? We can generate thousands of things. And what we want to do, right? We want to teach a neural network to recognize when it sees a circle and when it sees a rectangle. Just distinguish between them. Right, and we can generate as many samples as we want to just basically demonstrate to neural network how a circle looks like and how a rectangle looks like, right? So that's pretty cool. I really like this kind of exercises where you don't really have to worry about the data. You define how the data looks like, right? And it will maybe learn how to recognize this kind of things. So let's maybe define a couple of functions that generate like random circles and random rectangles, right? So let's say random circle, and you provide the Olivets canvas, like so. And in here, we're basically gonna take everything in here. Right, I'm gonna just put everything in here. And we're gonna only generate the circle. It would be probably nice to factor out this entire thing in here somehow. So maybe I'm gonna say random boundary, right? So it is going to accept the Olivets, and it's going to return probably x, y, width, and height. I think that does in fact make sense, right? So essentially x, since in C we can't return multiple variables, unfortunately, we have to use the pointers in here, like output parameters or something like that. Right, so welcome to C, I suppose. And the fun part is that somebody can potentially put a null in there and you will have a null dereference. And it's very scary. It's actually not, right? Null dereferencing is actually super easy to debug. Relatively, I think it depends, because at least it's super easy to find where exactly it happened. Because if you just accidentally dereference null, you can compile with the debug information, and in GDB you can know precisely the line of the code which tried to dereference null pointer, and then you can just do something about that. So dereferencing null pointer in C is actually not as scary as some people make it sound, right? So the scariest thing is dereferencing an invalid pointer. That is the scary thing. You are lucky if dereferencing an invalid pointer ended up being a segfault. You're freaking lucky if it's segfaulted, because you may have invalid pointer that points at a mapped memory, at a correct mapped memory, but the pointer itself is invalid or corrupted, but it points at something that is actually a valid, memory address, and it starts to like read and write into it, and it starts fucking destroying everything there. And the program is not gonna crash for a while. That's the most scariest thing. Dereferencing null pointers, fine. Segfaults, fine. Like if your program segfaulted in C, you're actually lucky. Seriously. People are afraid of segfault, but this is not actually true. They're not scary. They're actually helping you. They're telling you that you did something wrong. The scariest thing is that accidentally you have a corrupted pointer that points at a valid memory and you start fucking devouring everything in there, just fucking destroying. And it will start crashing in unrelated places, completely unrelated places. And debugging all of that is a nightmare. So especially the most annoying thing to debug is the stack corruption, right? So because then if your program will try to return from the procedure, it has a corrupted stack, but the return address is on a stack and stack is corrupted, so it starts jumping to invalid places and executing random shit in the memory, and your program just starts executing, like crashing in unrelated places completely. Right, programming becomes a game of probability at this point, random errors here and there, and nothing makes sense. Exactly, so that's the scariest part. Segfault, you're fucking lucky. You got a segfault and you know precisely why it happened. You're fucking lucky. Trust me, you're fucking lucky. One of the things that helps when you get into the situation when the memory gets corrupted is probably data breakpoints, I think. Right, so for example, the program consistently crashes because some value changes when it should not change and you don't really know why. You can put a breakpoint or basically break when at the place that tries to change that thing, and it will break at completely unrelated place, and that may give you a couple of clues, because I had situations like that, and it's still, you know, still gambling at this point. It's still gambling at this point. Imagine a cosmic ray fuck your memory up. Yeah, especially when you're trying to just play Mario. Classic. Anyway, so let's actually put this entire thing into a separate procedure. Alright, just to dub this entire thing. We're gonna put it in here, and essentially x, y, w, h. Do we need anything else? I don't think so. We can just do something like this, and then random, give me a random boundary, OC, x, w. So the code that I copy-pasted into the random boundary procedure, it's not going to compile, and I know that. I did that intentionally. I actually did that intentionally. It's a 5-head move by Zozin. Alright, so that works, and then we can do something like random rectangle. So this is going to be rect x, just x and y, w, h. Alright, so I know whatever the fuck I'm doing is not going to compile. I do that intentionally. I'm not even copying. I literally do that intentionally. I'm not copying, chat. I'm not copying. I do that intentionally. And this is why I was doing that, right? So I'm gonna go to the compilation errors and try to figure out what the fuck is going on. So here, maybe I want to call this x1 and y1 to just make it a little bit easier for me mentally to work with this entire thing. We're going to be returning x1 and y1, but x2 and y2 are going to be internal values, right? So also going to be returning w and h. Okay, so let's go to the compilation errors. So this thing, we probably have to dereference this thing. Probably what I want to do is query replace x1, y1 with a pointer to them, right? x1 has to be star x1, there we go, and y1 has to be star y1, there we go. And the same has to happen with w and h, right? So w has to be this. Well, that was funny, but I mean, Emacs doing a little bit of a fucky-wucky. H, freaking. It's case insensitive. It's too insensitive to the case. Freaking. Okay, are we gonna compile now? Well, hopefully. Fucking query replace. Should have not used query replace like that. If you want to query replace one letter, just don't do that, please. But I mean, we have a compiled language, so it doesn't really matter. OC. So OC, why do I even pass it there? I have width and height. Though I can actually do the following thing. I can accept width and height as arguments. I can do that. And that will enable me with something interesting. So essentially, when I'm calling this boundary with that, I can pass OC width and OC height. So that means the actual generation depends on not on the global width and height, but on the width and height of the canvas that we pass in here. So I think that's actually 5-head move. I do think so, chat. I do believe so. This is a 5-head move. All right, so let's go. What else do we have in here? So this is X and Y, so this is going to be just like that. Okay, and we have unused variable, which is not needed in a rectangle. It's only needed in a circle. All right. So I think we already reorganized everything. So we have two functions that generates a random circle, generates a random rectangle, and the time has come to generate the training data for our neural network. So let's actually come up with the neural network itself. Right, so we're gonna come up with an architecture for this entire thing. Obviously, we're going to have width and height inputs, right? And we're gonna have two outputs. But maybe we want to define, a constant that says how many shapes we have, right? So we have two shapes, and if we change the amount of shapes, the architecture of the neural network is going to change as well, right? So here we have this amount of things and this amount of shapes. So, and essentially, like, what kind of architecture do we want to come up with for such neural network? We probably want to allow the neural network to split its input into chunks, right? To split its input into chunks so that then it can do some logic based on those chunks, if you know what I mean. Right, so if we take a look at the size of the neural network, so it's size of the image, it's 28 by 28, right? 784. So the factors are this. So maybe this entire thing is divisible by 2 multiplied by 7, which is 14, right? So, and essentially it allows us to have chunks of the size 56 pixels. So maybe the hidden layer is going to be literally 14, right? Literally 14, because it's just like, it will probably then consolidate like different chunks into this, and it will be able to reason about like different sub-chunks of the image, right? It will be able to reason about different sub-chunks of the image because it has like a 14 neurons to do so, right? I don't know, I'm just like, hallucinating like different ideas. I don't really know how exactly the neural network is going to do that. Like, we don't know that. Right, and essentially once we have 14 of these things, maybe we want to be able to split it even more, right? So maybe 14 is actually divisible by 2. So maybe this should be enough, at least for now. Right, so let's just take this neural network as a baseline, right? So we have this thing which splits everything into 14 chunks, and then it splits everything in 2, and then makes a decision whether it's, a circle or rectangle or something like that. So, like, I don't really know how exactly it's going to do that, but it's just like roughly trying to come up with the architecture that kind of makes sense, right? Which kind of makes sense. Okay, so now, what do we have? When we're training, the training process actually accepts the neural network that it wants to train and the matrix with the training data, right? So how the matrix with the training data looks like? Let's take a look at that. All right. So let's take a look at that. So you have some sort of a neural network with its inputs and stuff. Right, so it has some hidden layers and then maybe some outputs. So, and essentially, maybe I want to actually use different colors for this entire stuff. So here's one color, right? So this is one color, this is another color, and the output color is going to be something else. So then layer, for the hidden layers, I can use something like this, and for the output layer, I can use something like that. So and essentially, you need to craft matrix where you have a certain amount of rows, right? So you have as many rows as you have samples, as you have images, and the first n column actually have a value of the input. They are the input values. And the next m columns, they are the output, right? And this is like a single consolidated matrix, and we need to generate this entire thing, right? We need to generate this entire thing. So that's going to be the data. So for the input, we're going to have 784 elements in here, and for the output, we're going to have 2 in here. So does it make sense? So the actual sort of width of this entire stuff is going to be 786. 786. So let's go ahead and try to do that. We need to maybe have a global constant that tells us how many samples we want to generate, right? How many samples we want to generate for this thing. We're going to start with something small. Samples. Let's generate 10 of them. Right. Maybe it's going to be actually samples per shape. So that means we're going to have actually 20 samples, right? So we're going to have 10 samples for circle, and we're going to have 10 samples for rectangle. Okay. Let's go ahead and allocate the training matrix after we allocate the neural network. And then alloc. So I'm going to be allocating in a global memory, right? So it's not going to be in a temporary allocator. Array len arch. So that should give me the neural network. So that gives me the neural network, which I probably want to randomize super quick, right? From -1 to 1, just quickly randomize this entire thing. Right. So then we are actually ready to allocate the matrix for training data, right? So the matrix with the training data, I usually call it T, right, for training. And let's allocate alloc. So the amount of rows is basically going to be samples per shape, but we have several shapes, so we multiply it by shapes. So that's basically what we have. Okay. And now, how many outputs we're going to have? So I think I'm going to take the input matrix of the neural network and take the amount of columns, right? And that's the amount of inputs, essentially, right? Essentially. And we're going to add the amount of outputs, right? So we're going to take this entire thing. And there we go. So, and if we change any of these parameters, this the size of the shape of this matrix is going to change automatically, right? We don't have to think about it, right? We explicitly basically set what these sizes mean, right? Okay, so let's start maybe iterating through all of these samples that we want to generate. So I'm going to be iterating from 0 to less than samples per shape. So, and we're generating, I suppose we're going to be generating pair of samples, right? So we're going to be generating pairs of samples. And within that single iteration, we're going to be iterating through each individual shape. We're going to be iterating through each individual shape. So what I want to do, I want to take a row, right? A matrix row of a certain thing. So essentially, I represent actually pair of samples. Right, it represents pair of samples, so multiplied by 2 plus j. So the actual sample is I multiplied by 2 plus j, because again we're going to be generating them in pairs. At least I decided so. Right, so one is going to be circle, another one is going to be rectangle, then circle, then rectangle. And the amount of samples is basically the amount of pairs of samples, right? So that's why I actually points not at the sample, not exact sample, but at the pair of sample. And the first element in that pair is circle, and the second one is going to be rectangle. Hopefully that makes sense, right? So we're just generating them in pairs. Right. At least that's easier for me to think about. And that should give us the row. And essentially what we need to do, we need to copy the image, right? So we can allocate all of the imagery, the canvas that we're going to be using for all of that, like here, and then basically decide what we want to generate, right? So we're going to be generating random circle. It actually will depend, I think. Yeah, it will depend on specific J, right? We can switch on J and what we're currently generating. So let's actually denote maybe 0J as circle and 1J as rectangle. In fact, this sounds like a job for enumeration, if you know what I'm talking about, right? So I think instead of like having shapes, it would be nice to have enumeration type. Maybe just enumeration. So shape circle, so in this one is going to be 0, and then shape rectangle, and then we can have something like count shapes, or maybe just shapes, and that automatically, you know, does everything we want. So after that we can say switch case, and this is a shape circle. In case of the shape circle, we're going to do random circle OC, and then we want to break. And then in case of random rectangle, we want to do rect. So as you can see, we're going to do this kind of switch. Depending on what iteration we're currently on, we're just generating random thing in here. So maybe it would be better to have some sort of like a table of functions in here, right? You know, virtual table like in C++. Right. So here maybe one of the things I want to do is just like if you accidentally got something that is not covered in here, just do assert unreachable. It will make sense if we increase the amount of shapes at some point. Maybe we'll want to add triangles, who knows, and then I will forget to modify this place. To be fair, I think the compiler will just tell me that you don't handle something in here, but just in case, I think it makes sense to cover you know, this case. Just say that's unreachable and crash, right? At least let me know that, like what's happened. Okay, so essentially now I need to take the submatrix of row and copy the pixels there. So let's do something like maybe canvas to matrix, right? And in here we're gonna accept the following thing. Man, I really want to be able to just take a submatrix of this entire thing, but maybe I can't do that, right? So I can do input. So the thing here is that row has amount of rows equal to 1, which makes sense, right? So a row matrix is a vector, right? So it means the amount of rows is 1. So that means we can just say that input is essentially the same thing, but with amount of columns equal to the amount of columns of the input, and that gives us like a smaller thing, right? Because when we take a row, we actually take only that specific submatrix, but then once I have this specific submatrix, I want to take this specific submatrix. So I keep taking submatrices. So because of that, the input is going to be just row, and then we reduce the amount of columns to the amount of inputs or something like that. Right, and then we want to copy the canvas, the pixels of the canvas that we generated in here into the input. Right, so that's what we want to do in here. Interestingly, let me actually put a certain here so I not forget, because I haven't done here yet. I still need to have the outputs, to do set the outputs. To be fair, setting the outputs is rather straightforward. I think it is in fact rather straightforward. Right, it's just like if J is 0, set 0th output to 1. If J is 1, set 1's output to 1, and we can just like fill them with 0. In fact, I can do that right now. I can just do something like mat fill row with 0, so I know that they're 0. And essentially, I can do mat at, I can take the row, the specific row is 0 because the whole thing is row, but the specific column is going to be input and then pulse, right, plus J, and I set this entire thing to 1. Easy peasy, lemon squeezy, we did it. Right, so the only difficulty is how do we convert canvas to matrix, right? So how do we convert canvas to matrix? Right, so, and what did I put in here? Right, so I take Olivet's canvas, which is OC, and then I accept the matrix, which is supposed to be row. Right, and since it's a row, I want to assert that row has the amount of rows equal to 1. This is cringe. Like the fact that this is very often situation, chat. This is a very often situation, and I noticed that long time ago, that on top of having generic matrices n by m, I quite often also have a row vectors. And like checking this kind of invariant at runtime is really freaking cringe if I'm talking about. It is kind of cringe. In fact, I think I noticed like yesterday or the day before yesterday. So in the definition of the neural network, there is, yeah, there is this thing. Yeah. I was thinking about that for quite some time. I even put it to do, right? So introduce separate type for row vectors. There are quite a bit of situations where we want to have specifically row vectors, but since we don't have them, we denote them with 1 by n matrices. Examples are biases and activation. Yeah, so for example, in the neural network itself, biases and activations are row vectors, right? And the way we pass activations through a neural network is the following. Right, so you have an activation, which is a row vector, and you multiply it by the weight bias. Right, by the weight matrix, I'm sorry. And then you add the bias vector. And that results, right, maybe we want to put something in here, right, to indicate. So this is the matrix, this is the numbers. And we end up with another row activation that we can feed into another weight matrix and so on and so forth, right? And the reason why I do that, by the way, this is a very much untraditional way of passing activations through the neural network, and we're probably gonna change that in the future. The reason why I do that is because I have a very specific mental model about matrices, vectors, and matrix vector multiplication. The way I multiply the matrices is the following, right? I take one operand of the multiplication, and then the second operand of the multiplication. Like this. Let's actually say 3 by 3. And I figure out what I have to multiply and add up by the intersections of columns and rows of these operands, right? So this is how I think about multiplication of this entire thing, and that's why it is easier for me to actually pass activations as rows. But a traditional way is to actually store activations and biases in a column vector. And a column vector looks like something like this. That's the more traditional way of doing that. And because people use column vectors, right? So you actually multiply them from other side. Right, so you multiply them from other side, like so. So here, it actually depends, the way you multiply matrices depends on their shape, right? Depending on the shape, you basically multiply them in different order. So if you use column vector for activations and biases, you're probably going to do something like this. And I suppose the reason why traditionally it is like that is because it just looks nicer on the paper. That's my hypothesis. I don't really know. I'm not a mathematician, but I think it just like looks nicer. Like look how it looks like, and look how this shit looks like. It's just like takes too much space. I think it's a little bit more compact. I think so. I think this way of doing this is a little bit more compact. But I like that you can think about this thing as passing activations from left to right. You know what I mean? Because the activations are on the left, so you're passing them from left to right, plus it doesn't mess up with my mental model of multiplication, so that's why I chose it like that. Right, but the traditional way of passing information is like this. Right, I do acknowledge that. I respect the traditions of mathematics, right? So the traditions of mathematics, to be fair, I don't know. You don't want to disrespect mathematical traditions. You really don't want to disrespect them. And here's an interesting thing. We probably going to be forced to change that notation. You know why? Because Fortran stores two-dimensional arrays not row-wise like C, but column-wise. It stores them column-wise. Right, which actually makes this kind of notation, this kind of way of passing the activations a little bit easier. And one of the libraries that I want to use in the future, LAPACK, for linear algebra and stuff like that, is implemented in Fortran. So to utilize these libraries for like linear algebra and everything, we probably will have to change the way we store the matrices. Right, because those libraries, if I remember correctly, they expect matrices to be stored column-wise, and we may start storing them column-wise as well. And since we store them column-wise, it would be easier to actually use this notation, the traditional notation. But all of that is going to be in the next episode. It's just like, you know, like a footnote. So yeah, but for now we're using like a row vectors. Maybe in the future we're going to have both row and column vectors. That would actually make sense. And yeah. So I think we need to introduce that because this is not like the first time I feel the need to have something like that. This is not the first time. So I think like I just need to fix it once and for all, right? So let's actually work on this today. So essentially here's the matrix, right? So matrix has rows and columns and has a stride for the same reason as why Olivet's canvas has a stride, so you can take submatrices if you want to. To be fair, it's rarely useful, but I mean, I just put it there. So, and let's define maybe something like a row, right? And a row is going to have only columns. It's not going to have a stride because stride is needed to find the next row, but you have one row. So, so we have only one row, and then we're gonna have elements in here. So this is gonna be the row. So yeah, this is the row vector. And the way we're gonna start refactoring everything, I'm gonna just return row on matrix row. So this is actually kind of cool. So you have a matrix, you can say, okay, return me a row, and we used to return it as a matrix with a single row, but now we can return it as a row, right? And one of the probably useful operations for the rows I can think of is probably going to be something like row slice. I really want to have a row slice. So here I'm going to pass the row. I'm going to also pass where the slice starts and the size of the slice. Or maybe something like len. And it will make it super easy then later to take this row, right? So we take in the row. We fill in everything with 0 and everything, and then say, okay, row slice, we slice in this specific row is going to be started from 0, but the size of this entire thing is going to be the size of the input. And then output is going to start at this thing. And the size is going to be, yeah, so this is actually kind of cool. And then we can have canvas to row. That's actually kind of cool. Canvas to row. Yeah, and it's just like, yeah, so that makes sense. And obviously this should not be a row. This should be a row, and this should be a row. Canvas to row. Let me see. It was actually called canvas to matrix. So this has to be a row, and has to be a row. And now we don't have to check that the amount of rows is 1. We don't care because we know that at compile time. Right, we know that specifically at compile time. So let me actually just ignore all of these things for now, and then we're going to do assert not implemented. Assert not implemented. So let's start compile assisted refactoring, right? So let's just go through all the compilation errors, but because we changed a lot of things, specifically we changed the signature of mat row, because there's a lot of code that uses a function, and all of that code expects this thing to be a matrix, but now it's a row, and it's going to break a lot of things, right? It is going to break a lot of things. But maybe before we go into compiler assisted refactoring and everything, we probably want to make a small break, right? Because I ran out of tea. Right, and it's better to do compiler assisted refactoring with a little bit of a coffee. Don't you guys agree? I think you agree. Let's make a small break, and so let's go ahead and try to compile this entire thing and fix all of the compilation errors. So let's go ahead and do that. Okay, mat row is supposed to return the row. All right. So we know that the amount of rows in a row is 1. That makes sense. So the amount of columns is going to be this. Stride doesn't matter because it's only needed to get to the next row. We only have 1 row. Right. And in here we take the pointer at where the row has to start, and this specific place doesn't make sense. Okay, so that's basically the whole refactoring that is needed in here. All right. And what else do we have in here? Okay, so when we're computing an end cost, okay, so that's actually pretty cool. So now when we take a row, the input is actually a row. This is so much nicer. Like, yeah. So we're being explicit what is the like a vector and what is a matrix, and it makes things a little bit more like easier to read. Okay, so and now we're trying to copy a matrix. So now this thing is a row, but input, yeah, and by the way, input is one of the activations. It's actually zeros activation, and it has to be a row as well. Right, so I think one of the things we have to change in here is just like make activations and biases row explicitly. Why didn't I do that earlier? That makes so much sense. Right, so, and that's basically, yeah, that's basically what I wanted to do in this original to do, right? Okay, so let's actually go further. Okay, when we're allocating matrix alloc. I'm thinking I can actually, so I need to probably implement row alloc, but do I really need to implement row alloc? Because I can just take the zeros row out of the allocated matrix and that's it. Right, because allocation just allocates the elements. The area with the data stays the same, we just change in the metadata. Yeah, I can, like, I don't even need this kind of thing. Well, I mean, I can probably do something interesting, right, can't I? So I can turn it into a macro, so to speak. So essentially, I can say row alloc. Obviously, it's going to accept the region, right? So because we're going to be located in the region, but it's going to accept only the columns, and we can turn it into a macro, right? We can turn it into a macro. So essentially, we're going to allocate a matrix in a region with a single row with this amount of columns, and then take the zeros row out of that, and that's basically the implementation of row alloc. That, okay, so this is kind of interesting. Rows, the vectors, are basically a subset of matrices. They are a subset of matrices. Maybe we can implement row versions of matrix separations, like this one, through the matrix separations themselves. Right. Because, for instance, like I want to have a random row. What I can do, I can probably have some sort of a conversion, row as matrix, which accepts the row, but returns the matrix, because it's super easy to do so. Yeah, that's actually super cool. Okay. Because how do you even do that? So the width, actually the rows is going to be 1 because it's a single row. The columns is the amount of columns in a row. The stride, since you have a one thing, you can just basically set anything, right? So we can just set the same literally stride. And in terms of the elements, it's the rows element, right? And that's it. So, and if you want to implement row random, which accepts row and low and high values, you can essentially implement it as matrix random by taking your row and converting it into a matrix, low and high. Right, because these structures, they act like references, right? Because they store the reference to its elements. We reinterpret row as a matrix and use matrix separation on it. That is so cool. So row is a subset of matrix, and we can exploit that. So we can reuse the same. We don't have to re-implement these operations, actually. we really don't have to reimplement them. So we just need like one operation, like row as mat, to take a row and convert to a matrix. And another one that we need is probably mat row to convert matrix into a row. That's actually super cool. I like that. What the fuck? Why is this so straightforward? Like, I didn't expect that. But this has advantage of being explicit about this thing having one row at compile time. Right, and that's actually very important for me, right? It just like gives you more information at compile time generally. Okay, so what do we have in here? And yeah, so now we can essentially say, so here I can just do row alloc, and I do arch 0. There we go, row alloc. And for the BS, for the biases, this is a row alloc, and we don't have to provide this one in here because that one is provided automatically by row alloc itself. So here is this one that we just removed. That's so cool. So since row is subclass of vector, it just like works automatically. It's just like inheritance in C. Yeah. It's basically inheritance in C. Right, so let's continue. Okay, the row alloc, yeah, we have to do that within a specific region. Okay, when we fill a specific matrix, can we do row fill? Do we even have a row fill? No, we don't. Row alloc. So that means we can grab matrix fill and just do row fill. We take the row and X, and I just reinterpret row as a matrix, and I fill it as a matrix. This is so cool. What the fuck? Why this shit excites me? Like, it's just probably because this kind of stuff. People usually think that this kind of stuff requires a complicated high-level language like C++ and Java with inheritance and stuff like that. And it's just like, no, you can do that in dumb C. You can do that in dumb C if you need to. And it's basically like inheritance if you think about it. It's just we explicitly converting one type to another, but we're reusing the same operations, right? So the only reason why it works is because from the type point of view, row is a subset. Row is a subset. So people don't like macros, I guess. But yeah, yes, somebody said that in the chat. So, but the question is, why people don't like macros? Is that because they legitimately spent some time implementing their own macros and they came to a conclusion that they suck, right? And you should never use them, and super dangerous. Or is this because the professor told them so? The professor in the university who's teaching them Java and OOP told them the macros bad. Maybe that's the reason. But that raises another question. Why the fuck are they listening to that professor? Who probably doesn't even have experience in the industry. Why do they listen to them? Probably because they paid for the course of the university. So the reason why people hate macros is literally because they paid for it. So it's a sunk cost fallacy. Because if they don't hate macros, they will admit that they wasted money. What the fuck is this logic? But anyway, whatever. Forget everything I said. I think it doesn't matter. So I went too deep. I'm sorry. I didn't mean to go that deep. So let's continue. What do we have? Okay, so printing. So we also need to have a row print. Okay, so let's find a matrix print. Can we utilize the same thing? I think we can. Right, as long as we don't really repeat a row argument 2 times more than 1 time, we can basically proxy all of these things. So we can do row print, matrix name padding, and here, row, so this one has to be a row. Row, fight the power. So row name Exciting. There we go. What else do we need in here? Forwarding. Yo. But we don't really use mat dot anywhere else. I don't think we need to proxy. Yeah, so the only place where we use mat dot is nn forward. So essentially, for all of these things, we can do row as matrix. It's kind of cool. Yeah, we can have just one operation, matrix dot. And if you want to have different combination of vector matrix, vector vector, matrix matrix, you just convert to the appropriate things, right? So you have one vector and one matrix, just convert that vector to a matrix and do multiplication. And since all these structures refer to their elements, it will just work. So that gets rid of, you know, copying the code, right? Because quite often people just copy different combinations, vector, 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 matrix, 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 right? So here we can have just matrix, matrix, and you can just convert between these things. It's actually so cool. Really like that. Isn't that cool? I think that's pretty cool. So, okay, so in here, this is a row as matrix, and here is a row as matrix. Both of these things are matrices, so it's gonna be fine. And when we are activating this entire stuff, we're doing it like that. Okay. So almost every argument is actually wrapped in row as matrix, except the weights matrix, but that's fine, I suppose. That's fine. So let's continue refactoring. And then dot input. Okay. Row copy. Did we already define row copy? I think we didn't. So let's take matrix copy. But do we want to have it? Yeah, I think we do want to have a row copy. I think that makes a lot of sense. Row copy, dst src, and then in here, mat row as mat. Okay. Okay, so we have a special macro that accesses the elements of the matrix. Maybe we want to have a similar one for the rows as well, but it's going to access only the columns. So where is the row? Let's define row at. So it accepts the row and it accepts the column, and then we can say row elements column, I suppose, right? That's it. So I think we need anything else. If we take a look at the matrix add, it kind of needs to exist because of this kind of situation, because it's super dangerous. But for the row, it really shouldn't exist. But I still want to have this macro because then it makes it super easy to refactor things like so, right? I can just replace matrix add with row at and just like remove 0, and that's the same code. So it just makes it easier to refactor, even though there is not that much reason for this macro to exist, because the reason why mat add exists is because it's super easy to make mistake in here. It is super easy to make mistake in here. When you're working with a row, you can't really make any mistakes in here because, yeah, so the column is basically the element. But it just makes it easier to refactor from mat add to row add. So yeah, I think I'm gonna introduce this thing. So because it's just like easy to refactor at some point. So we compute in the cost, and we compute in the difference between jth column of the output, and yeah, that makes so much sense. That is cool. It's very straightforward. I really like that. It's very straightforward. So when we copy in, yo, look at that. Row copy. Yeah. So you have a neural network, you take an input for that neural network, which is a row, you take ith row out of the training data and you copy it into the input, and it's just like very much type safe in the sense that like it only works with the rows. You cannot just work with arbitrary matrices in here. Yeah, it's just like, that's so cool. What the fuck? So I should have done that like way earlier, right? So we're filling up a row in here, so it's super easy to replace it like this. Oh, okay, so we have a little bit of a conditional compilation in here, which means that maybe we want to repeat that here as well, but this part is not compilable, at least right now. So yes, since we changed and we have to remove these zeros because, I mean, there's no row. A row literally doesn't exist. And we probably can guess how the code is going to look here because the outputs are rows. We can just like replace them like so. There we go. So that's pretty cool. And in here we do row. Row. Yeah, it's kind of funny. Like in all of the place where we want to rename mat add to row add, the row is always 0. The row is always 0 because they were rows in the first place. That's why this first argument was always obsolete. That's why we had coded 0 in there. And that had coded 0 should have been probably like a red flag for me, but I don't really know why it wasn't. You know what I mean? Like why? Huh. It makes so much sense. Oh wow, okay. Since biases were always a vector, this loop, and I think we wrote this loop since like first episode or second episode, this iteration was always 1. This iteration literally should not exist, right? Because this thing is a vector, so rows is always 1, right? This loop shouldn't exist at all, so that means here row, like this. It's actually, that actually even simplifies the code. What the fuck? Like introducing this specific thing even simplifies this thing even more. What the hell? Am I on the right path? Another one. Freaking another one. So when shit like that starts to happen, when I'm literally removing the code, I feel like I'm on the right path. You know what I mean? I think that's the indication. It's just like playing a video game and seeing an enemies. So that's how you know that you're in the right path. So similar in here, like you're trying to refactor and you end up removing code. Yeah, so you're on the right path. So maybe that was the right abstraction. It's just like the abstraction hit the right spot. Just the right abstraction. Know what I'm talking about? I'm pretty sure you know what I'm talking about. Right. Okay, so, and yeah, so we have to replace this row with just that, and so all of these are, and this would be funny if the entire thing just breaks. If I modify too much and this entire shit is not going to work, like, at all. Okay, another one, another useless iteration. So let's just quickly do something like this. So this has to be row, but I hope it's not gonna break. Right. Defiant. Wait a second. When did I write this code? I think I wrote it at the beginning of the stream. So yeah, this is for how long this typo existed. But since we're using statically typed compile language, it doesn't really matter, because at the end of the day, the compiler will just tell us, right? So, yeah, so the thing is that when I program in such languages as C or like any statically typed languages, I'm having a conversation with the compiler. I feel like a lot of like beginning developers have really adversarial relationship with the compiler, right? So they constantly are being afraid of the compilers. They're just trying to fight with the compiler, stuff like, no, you're having the conversation with the compiler. Right, which is just like with ChatGPT, but actually smart. So compiler is like ChatGPT, but deterministic. Yeah. So programming languages are deterministic ChatGPTs. Not all of us have taken a compiler class. Me too. I never been in a compiler class actually. So the whole CS course in my university was certain algorithms in Delphi. So yeah, not all of us been in a compiler course, including me. I never been in a compiler course, compiler class. Honestly. All right. So let's continue. What do we have in here? So What are you a token? Too few arguments. This is because you're supposed to. I think we fixed the whole thing. Delphi, how old are you? This is a wrong question. If you use Delphi, it does not necessarily tell you something about my age. You first have to ask, where are you? And if I tell you that I'm in Eastern Europe, I don't know. To be fair, like maybe I am old. Maybe we already switched from Delphi to something else, right? I don't know. You are in Asia. Well, I mean, at some point, so it's the Eastern Europe where I am is so eastern, it's basically Asia. That's how Eastern Europe is. It's the eastest of the eastest Europes. It's Asia. Yes. Anyways. What do we have? What the hell is going on? Yeah, so we have to provide the region in here. We're gonna be allocating it in a constant memory, in persistent memory. Very, very Eastern Europe, yeah. Asia. All right, so row fill. Okay, do we need anything else? Canvas to row. Implicit declaration. Why is it capitalized? Who capitalized on my names? So this is just a row 0, and that should be fine. Unused out, and this is because I have to do just. Oh my god, that just makes everything easier. Right, so I can even do the following thing. I can say row fill out with zeros and then set j neuron to 1, and j indicates the specific shape. It makes everything easier. Why didn't I do that earlier? Because I didn't know any better, right? So essentially, if you're like making mistakes, you're not really making mistakes. You got an information. When I only started developing this entire thing, that was not really obvious to me. So I had to develop it for quite some time for this abstraction to emerge or whatever. A row slice, right? So we don't have a row slice. Let's implement that. So we're going to be slicing the row. So one of the things we probably want to check. So we need to check that I is even valid, right? We want to assert that I is less than amount of columns with the row. And length can actually go overflow. We also want to check that. So plus length should probably be right. So the thing that you point at, because I plus len can still overflow. So we have to do -1 less than columns. Or we can just do it like that, right? That kind of implies -1. So, and then we return the row. We return the row with the columns that we provided in here. Maybe we should call this thing columns, right? Maybe that should be called columns. And then the pointer is basically row at I and pointer to that. So we're slicing the row. We're slicing the row. That's pretty bogus, I think. Let's find the declaration and rename len to calls, because I think it does make more sense. Yes. And it freaking works. But I would like to go through all of the demos in here, right? Because some other demos actually got broken. We made a lot of changes. So let's actually try to fix Zor. Let's go ahead and do that. Told you. Okay, so now this entire, yeah, this is pretty straightforward. We're just replacing mat ads with rows. And so this one, ooh, this one is interesting. When we're doing activations, yeah, so this is already not a framework. This is a gem, not the main framework though. This is basically the framework on top of the framework. It's called gem. It's the thing that provides the UI for the demos, right? So the framework itself is just like for, you know, training models. It doesn't provide any UI, but then you have a thing on top that allows you to do these kind of things. right? It basically shows things you can control, you can plot things, and so on and so forth. So this is provided by a separate library on top of an Android called the Gym. Right, and it uses Raylib to render everything. So something got broken because of our recent changes in Gym as well. And this is because we have a widget that renders the activations of the neural network as a heat map. So what does, okay, this is a good question. What does mat field ES stands for? It stands for elements. But you know what? I think I should rename it to element. This is a good question. Thank you so much. Let's actually rename it to elements. Like literally. You know why? Because I refer to this field only in macros. I never refer to this field directly, or very rarely. So it doesn't really make much sense for me to shorten it up, because I don't really type it very often. It's inside of macros anyway. But by making it full, it can become more readable. So for example, you wouldn't have any questions if it was like that. And it doesn't really cost me that much to call it a full name, because I don't type that name anyway, because I'm referring to this thing through row at and mat at. So that's a good one. Thank you. All right. The variations are menu of the reader. I have nothing against abbreviations when they do make sense. For example, when you have to type something very often. When a certain name needs to be typed very, very often, I may shorten it up to a single character, yes. But, like for example, in this specific case, I do not plan to type it very often. I do not plan to type it at all. I can actually make it a bit longer. So it all depends. It all depends. Okay, so, and, all right. So we broke the widget that renders the heat map as activation thing. But is that really even a problem? Right, it calls to render matrix as a heat map. But vector is a subset of matrix, so that means we can take the row and convert it into the matrix, and we can use the same trick. Right, it's just like I don't have to re-implement anything. It's gonna work. All right. So now we're, rendering image grayscale. So this one is really interesting. So it accepts the neural network, and it accepts pixels, like literal pixels. So what it does, it basically treats the neural network as having at least two inputs and at least one output. And essentially it iterates coordinates of the image and feeds the coordinates into the inputs, and it takes the outputs and sets them as pixels. So it allows you to take the neural network and plot its, latent space. Right? It's used by the image interpolator, right? And it's a widget that you can slap on the UI, and it can see what the neural network dreaming about right now. So I can even demonstrate that. So the thing that renders these dreamy images is that widget. Right? So that's what it is. So we can, I wonder if we can just find image to, here it is. There we go. So if you start rendering, so this stuff, this blobby stuff is rendered by that image. So it takes the neural network and tries to render it as an image. So that's basically what it does. Okay, and in here, yeah, so we just need to change, because the inputs and outputs are rows now. We're feeding coordinates of the image into the inputs. So the outputs are going to be just that row. It's just a single thing. Okay. So let's go through other compilation errors. What else do we have in here? Okay, so all of the usage of yes is within the library itself, right? So I think that should be fine. Elements. 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 Maybe I should just query replace m-es elements. Query m.es m elements. That should be it. So there's another thing in here. Another one. Compiler assisted refactoring is doing things. Who needs IDE to just rename a single variable? You don't need IDE for that, right? You can just use a compiler. Unless you're using a scripting language. But even in case of a scripting language, it's not that big of a deal, I think. Right, you just need to have unit tests. All right, so this is element. Okay, so we're using this thing outside. Ah, but that's fine. Okay, I think we are done with Zor. Let me see if we didn't break Zor. Right, so demo Zor. Does it look broken? It doesn't look broken, looks fine. We made a lot of changes, we didn't break anything, which is good. Which is absolutely a good, absolutely good. So now, let's go ahead and fix the adder. Let's fix the adder. What do we have in here? So, okay, so we're referring to this entire stuff like so. Row. So the main changes that we have to make are essentially mat add to row add. Okay, so here we're referring to this explicitly, but I think maybe at some point we're gonna get rid of these things as well. We'll see. Okay, so the adder is fine. It compiles at least fine. So let's add the adder. Oh yeah, I just like ran it in the wrong place. It couldn't find the font. Right. So now it found the font. It's kind of funny that it picks the default font if you can't find it. It looks alright, so it doesn't look broken, at least. That's cool. Alrighty. So now let's go to the image to NN. Right, so we need to fix the last thing in here. Row. So yeah, so majority of the changes are just like mat add and row add, which is good. So that it's nothing super serious. Okay, that was fast. So that specific thing was super fast. So now image to NN. It seems to be working. Seems to be working. All right, look at that. Yo, and we can interpolate between them. That's cool. Everything's working. I think the time has come to do a committee. Yes. So we did a pretty serious job, right? We introduced a separate types for row vectors, right? So this is super important. I'm going to just commit this stuff. I'm not going to commit the shape stuff yet because it's not finished, but I'm going to commit this specific thing. Introduce type for row vectors. Right, this is super important. It's going to be super useful in the future. Is there a playlist for watching this project from the beginning? Yes, go to the Tsodin Daily channel and click on the playlists, and the playlist is called Machine Learning in C. Right, so I could give you that thing, but YouTube is kind of slow for me when I'm streaming, right? Because I'm streaming from my old laptop. Right, so the playlist is going to be in the description, right? So usually for each individual episode on YouTube, the first thing I put in the description is the link to the playlist of the entire series, right? So you can basically search from the beginning. So let's enable again the shape demos. Right, let's enable again the shape demos. So that's fine. And this thing is not implemented. Okay, so we're finally ready. We spent some time refactoring things, but I think refactoring is part of the experience, right? I think it's part of the experience because discovering, in my opinion, discovering this row vector abstraction is kind of important. Right. So we're ready to take the canvas, the Olivet's canvas, and convert it into the row. One of the things we probably still want to check is that OC width multiplied by OC height is equal to the row columns. Right. So essentially, you have the same amount of pixels as you have columns. That's very important, I think. It's very important. So let's start iterating the pixels. We're gonna iterate them row-wise. OC height plus y, and we're gonna be iterating columns now. All right, so this is gonna be columns. And now we have Olivet's pixel. And what's interesting is that Olivet's pixel is kind of similar to mat@. I think they even defined very similarly. Olivet's pixel. Yeah, it's literally the same idea with the stride and everything. It's kind of funny how the matrix from nn.h and the canvas from Olivet's, they're very similar. It's just the canvas is a matrix of integers, a matrix of pixels. And in nn.h, it's a matrix of floats. But overall, they're like similar entities. They're very much similar entities. It's kind of cool. But I mean, it's like, it's obvious in the inside. But still kind of cool when you're working with that and you're just like realizing all these things. So we take the canvas, X and Y, and this is the current pixel. And we need to figure out basically the index within the row. We can say that this is Y multiplied by width plus X, and that's the index within the row. We can do row at row I, but that's not it, because this is a pixel, this is 32-bit integer, but we need to convert it first of all into brightness. Since I'm using primarily black and white, and I do that intentionally, by the way, I use black and white, I can just pick any component of the pixel and call it a brightness, right? So it doesn't matter, we can pick red. So the easiest way to pick red is probably just do bit end and just like take the first byte out of here, and this is basically, we're gonna call it a brightness. Then we need to convert it from 0 to 155 to 0 to 1, and that is super easy. You just convert it to float and divide it by 255 float. And that's it. That gives you the brightness of this entire thing, and we store it into the row. Though I'm not sure if it makes sense to actually do it like that. So maybe I'm gonna inline it so it looks nice like a single thing. We can clearly see that we're copying one thing into another one. Right. So that basically it. That is basically it. Do we need anything else? One of the things I wanted to do, I wanted to standardize what kind of colors do we use for background and foreground. So let's do the following thing. I'm going to introduce background color, and we're going to use black as the background color, and foreground. For the foreground color, we're going to use white. So, and let's quickly query replace when this thing with a background color, like so, and query replace this thing with the foreground color, like this. So then, since we have a centralized place, it will be super easy to just like change it everywhere, right? I think that makes sense. I really like centralized places for all of the magical variables. And I like to have a lot of magical variables, because then that place where you store, where you manage magical variables, effectively becomes a config section for your program, right? It becomes a config section, which you can then maybe factor out into a separate file or something like that. All right, and you can just like iteratively grow that config section over time. Okay, so canvas. I think that's it. So canvas to row, we just like converted canvas to row, and that generates everything we want it to generate. So let's rebuild the entire thing. Let's rebuild the entire thing. What do we have in here? So this is I. Oh yeah, I'm an idiot. I'm supposed to actually do it row. Yeah, so first comes the row and then the index, and index is computed based on that. Okay, that is cool. That is very, very cool. Okay, so let's run shape, and it just generated output, but it like didn't really do anything. So it generated the input. What I want to do, we probably don't need the entire thing in here, right? So here's just the input. Here's just the input. Let's print it, right? Let's print the entire training data that we generated. So we spent quite some time refactoring things and crafting this entire thing. Let's take a look at it. I think the time has come. So it's probably going to be huge because it has like very wide rows, and we're not going to be able to see anything interesting or useful in there. Okay, yeah, that's too much. We can't see shit in this mist. Are some of them even one? Yeah, okay, some of them are ones. We can at least see that. Yeah, some of them are zeros, some of them are ones. So that's cool. Let's do the following thing. Let's actually try to iterate through all of the rows of this thing. This is so pleasant, isn't it? Look at that. You have a matrix. You iterating through rows, and you take an ith row, and you have a row. The separate entity as a row, and you can have row operations, just like... Isn't that cool? So the cool thing is that I didn't intentionally design this API to be like that. It kind of evolved by itself like that. It was just like solving specific problems and trying to see patterns, and then compressed patterns, and it's just like, yeah. Row. Fight the power. Yeah. Anyway, so we can try to interpret this entire row as an image, right? Specifically, we can take it as an input, maybe. All right, let's do input, and this is going to be a row slice, a row starting from 0, but we're going to take the input columns, right? So we have that. So we take specifically input part, not the output. We don't really care about the output. And for the, we can take the output part. I think it could be useful. The output part is something like this. I can't see scheiße in this mist. So what I want to do, I want to iterate, I want to turn the row back into image, just to check that we did everything correctly. Right, so we took the image, generated the image, then converted it into a vector, and we converted it back into image just to see like what's going on in there. I think that makes sense. I'm going to be iterating by rows, then we're going to be iterating by columns, like so. And essentially, I'm taking row at input, y multiplied by width plus x, so we have that, and we want to print this entire thing with a space, right? So we want to separate them, and each row we're gonna put a new line in there. Yeah, and maybe at the end in here I want to print row print. We don't even have a row print, but we can easily implement all of that, right? So row print out should be as easy as mat print, and just like row as mat. I'm too lazy to go to an n.h file. Right. That's why I'm gonna just like hardcode this entire thing. Honestly, can't see shite. I have an idea. What if we do the following thing? Okay, so if this specific pixel, right, but let's call it brightness. If brightness equals 0, just put a space in there. Otherwise, if it's greater than 0, let's put this thing in here. So hopefully, since I'm setting 0 explicitly, it's going to, maybe I can do something like this. If it's less than some sort of epsilon, which is like 10 to the power of minus 6 or something like that. Yeah, I think that makes sense. So at least we're gonna be able to see something. Okay, look at that. So this is the circle, this is a circle. Maybe we need to make it wider, right? So let's actually put additional things. So it's going to be white boy pixels. Okay, so here is the circle. and the output vector sets 1 to the first element. Here is the rectangle, and it sets the output second, neuron to 1, right? So this vector indicates the class, right? If the first neuron is set to 1, that means it's a circle. If the second one set to 1, that means it's a rectangle. So that's basically all of the data, and we're ready to feed that data into the training process and train this entire mother flipper. Are you guys freaking ready? I think you guys are not fucking ready for this kind of shit, but anyway. So we're gonna start training this entire thing, but I like to have like an actual UI for training, right? So we're gonna start ArrayLib. But unfortunately, I ran out of tea and I'm already streaming for 2 hours. So I usually don't like to stream more than 2 hours, but we haven't finished yet. So I think we're gonna go for 3 hours. This is gonna be a long 3-hour stream. How about that? But before go into the UI part, I think we need to make a small break. So let's just go ahead and start using Gym, right? So the way we do UI with this framework, we're using Gym. So let's include a gym.h, and it's also a single header library. So we have to do Gym implementation. So let me quickly turn off the music, right? So Gym implementation, and it also includes ArrayLib. So first thing we need to do, we need to initialize the window. So let's start with maybe 16 by 9 and multiply it by a certain factor. So, and the factor is going to be, I don't know, 80. I think that's a good factor. And the title is going to be shape. So after that, we probably need to set target FPS, and it's going to be 60 FPS. We're going to be training our model at 60 FPS. And while window should not close, right? Window should not close, we're going to begin drawing. We're going to start drawing, and then we're going to end drawing. So the thing we're going to do in here, we're going to clear background with, I think I introduced the Gym back, yeah, I introduced Gym background. All right, so there we go. So we have this thing. So, and after that we can close the window, though I don't think it's necessary. Let's recompile this entire thing, and that should basically create a window and on which we can put widgets and stuff like that. So, okay, so we are conflicting with STB, but to be fair, I don't use STB anymore, so I can remove it. So we don't have to conflict anymore. Where's the compilation? There we go. So, yes. So what we need, the first thing we need is probably be able to plot the cost, right? So to be fair, I could visualize the neural network itself with the heat map and everything, but I don't think it's particularly that useful, right? So it's going to be just like one huge matrix and one smaller matrix. We can try to do that, but I don't think it's going to be very useful. So we need to get gym rect, and let's say this is going to be root. It's initially going to be 0. So, and its width and height is going to be render width, the current render width, and render height. So this is going to be our sort of like a slot that takes up the whole window. So after that, let's find the thing that visualizes the neural network. So gym render, we can just like visualize it in a classical sense. Just provide that and provide the root and just see how the neural network looks like. I don't think it's going to be that particularly useful. There we go. We can't even see that. It's pretty funny. That is weird. Why can't I see that shit? So if I use a heat map, weights heat map, right? Weights heat map, and I just provide the root. So is it going to be something? Something got broken. Something got broken. Root.h. Oh yeah, thank you. This is the second reason why I didn't stream more than 2 hours. There we go. So this is how a neural network looks like. Not particularly useful. Right, so there's so many inputs, almost 800 inputs, and they just look like a single bar. And these are the connections. Oof. Yeah, oof indeed. So it's not particularly useful. Instead, we usually use like weight heat map. But even for such neural network, I don't think even visualizing this entire stuff is useful. Right, so we're probably not going to do that. We're not going to visualize the neural network at all. So let's introduce the plot, because we're going to be plotting the cost function. So as far as I know, it's just like gym plot. So this is the plot. And we have a special widget, gym plot. And we're going to be simply rendering the whole thing in here. Plot root. Okay, so here's the plot, so here's the 0 and stuff like that. So we may want to start batch processing, or how is it called, like STG. Stochastic gradient, SGD, stochastic gradient descent. So let me find, so there is batch process. So to do the batch processing, we need to have a region. So we're going to be allocating stuff in a temporary region. We also need to have the batcher, the thing that splits the input data into batches. Right, so it's a special entity that is needed in here. And here is an interesting thing. We need to pick the size of the batch, right? We need to pick the size of the batch. So let's say that maybe the batch size is going to be, so we have only 20 samples. Let's say that the size of the batch is going to be 5, right? So we have like, you know, a single batch is going to be 5. Then we provide the neural network itself and the training data, right? So this is the T training data. And rate, let's define the learning rate somewhere up there as well. Float rate is going to be 1, right? Because we're going to be using the sigmoid stuff, and with the sigmoid learning rate 1 is fine. And we actually want to process several batches within a single frame. Because of that, I like to put that in a loop. And in a loop, we're going to have like batches per frame. Plus I, and we can just process that. So batch structure has a very important field. So let me see. It has a field called finished. So if this thing got finished, that means we've finished the round of batches. So we finished one epoch. So that means we need to take the cost, the average cost of the neural network now, and add it to the plot. Append, so where's our plot? So this is the plot, and we just like appended it in there. And that's basically it. One of the things I like to do as well is basically shuffle the rows of the training set to make the whole thing stochastic, right? So we're gonna do shuffle rows of T, and that's basically it. So that's the whole thing. It would be also nice to have the paused variable, right? So while the whole thing is not paused, and we can start the application while being paused, right? So paused is true. And then if key pressed key space, we're gonna simply toggle the post. So pretty straightforward. Pretty straightforward. So that's the whole thing, actually. That's the whole thing. And it's going to render the plot. And let's see how the plot is going to go. I think it's is key pressed. Yeah. Batches per frame. Bat chest per frame. So let's say size T, bat chest per frame. How many of them do we want to have per frame? So if we're going to have 20, 4. So that means we're going to handle all of the samples within a single frame. So since we don't really have that many samples, maybe it's fine. Maybe it's totally fine. Who knows? Maybe it's totally fine. All right, so we're ready to start. and it learned something. It actually learned something. But how can we verify it? Like, what the fuck did it just learn? How can we verify? So when people write classifiers, right? When people write classifiers, one of the problems that they can face with is overfitting. So what is overfitting? It's when your neural network becomes very good at recognizing your specific training data, but anything outside of the training data is actually like it fails miserably. So it's called overfitting. Like it works only on that training data and it fails to generalize completely. To combat with overfitting, people usually introduce another metric, which is validation cost. So essentially, as you can see, we generated a bunch of training data, right? We generated a bunch of training data. What people do, they completely separately generate another verification data. And they never show that verification data to neural network, never show that. The neural network shouldn't even know about this thing. Right, they train on the training data, and in parallel, they check the cost of verification data that the neural network never saw. And what's interesting is that at the beginning, they all gonna go down, but at some point when the neural network will start overfitting, the verification cost will go up because the thing works really well on the training data, but fails miserably on verification. So this is one of the things that we want to check. We didn't need that before. We didn't need that before because the models that we trained before were supposed to overfit. That's very important, right? If we take a look at the things like Zor demo, right? So this is going to be Zor. You have 4 samples in the entire training data. You're supposed to overfit them. You're supposed to like be perfect on that amount of samples, and there's nothing more. So that's totally fine. Overfitting here, it's supposed to overfit. If we take a look at the adder, adder is another sort of neural circuit. It also supposed to overfit. So this is the entirety of the training set, and it overfits, right? It's supposed to overfit all the time. So that's what we expect. The thing with image interpolator, it's also supposed to overfit because we're trying to replicate the images that we have in here. So we never really needed that verification technique because everything is supposed to overfit. Here, this is a completely different story. Right, so the thing may start working really well on the data that we showed, but it may fail on the data that we never saw. To avoid overfitting, you need more data and more general data. Yeah, so the more data you have, the less you're gonna overfit. Because essentially, if you have the data, the full data, all of the possible situations, and you just overfit on all of the possible situations, you basically generalize this thing, right? I'm not the machine learning guy, but because you're generating training data, it seems easy enough to just generate new training data instead of shuffling input metrics. Yeah, this is actually true, right? So this is a good comment. We can do that, but I wanna pretend that this is not generated data. Right, because I'm sort of practicing, right? Because at some point we're gonna take our code and we're gonna slap it on something like MNIST database, right? And something like MNIST database, and I want to kind of sort of like pretend that this is basically MNIST database, and I'm just like have a limited amount of stuff. That's what I'm doing. But regenerating the whole data could have been an interesting technique to actually improve the performance of this entire stuff. Yes. That's actually a very cool idea. And we're probably going to do that at some point. But for now, I just want to like pretend that this is sort of like a MNIST database or something. Okay, so let's actually take this entire thing that generates the training data and factor it out. So generate samples. So maybe we're going to actually return the metrics. Generate samples, and here we're gonna accept how many samples we want to generate. Oh yeah, somebody actually mentioned a very interesting thing. Let's say you don't have access to any more data, but you can manipulate the already trained upon data. Is editing the old training upon data enough to avoid overfitting in general purpose model? It is a thing. It is called data augmentation, right? So it's literally a technique that is used by machine learning people. So essentially, in case of images, you know what they do? If you need to classify like animals, like dogs and cats and stuff like that, they resize images. Like they take the actual data, they resize of the images, flip them, rotate them, those generating more data from the same data. So by rotating and switching around and stuff like that, they actually expose the neural network to more aspects of the image. So people do that, right? So it is an existing technique, data augmentation. Yeah. So that's actually pretty cool. Some color transformation also help in some cases. Yeah. So I know that because I was like sometimes looking at APIs of machine learning and stuff like that, and some of the existing libraries, they even have like things to automatically augment the image data, right? So they can automatically do that for you. You can give it just like a set of pictures and they just like apply different transformations and give you more data. Right. You do that so that the neural network don't learn the specific configurations of your input. Yeah, exactly. So the more data, the better. The more data, the better. Okay, so let's generate some samples. So here I can just like move this entire thing to here and return T. So let's just try to compile and follow the compilation errors. Okay, so where is the build.sh? Okay, so it accepts n, but it's an input stuff. I suppose I can pass a neural network in here, but I don't really use the neural network for, though it probably, yeah, I don't want to do that. So I think I'm going to explicitly say something like input size, and the input size is width multiplied by height, right? So that's the input size, and output size is the shapes, like how many shapes we have. So this is samples per shape, and this should be replaced with just samples, right? Because we specify how many samples we want to have in here. Then we have stuff like input size. This is output size. There we go. So we're also allocating this thing in null. Right, but maybe it would make sense to supply the region. That would have made sense if we want to apply the technique of regenerating the training data every single time, right? So if we're generating training data on each batch, if we're doing that, we probably want to do that in a temporary memory. So I think it makes sense to supply the region in here to make it more generic in that sense. So this is going to be input size, and this is the output size. Maybe we can even pass input size and output size from here, but it's fine. All right, and then we just return this entire thing. Okay, what else do we have? So OC, it needs to... Oh, that is very interesting. It needs a temporary thing in here. It needs a temporary thing in here. So essentially, we can try to allocate this thing. Yeah, we need temporary allocator. So the matrix that we return from here has to live longer than the temporary OC that we're allocating in here. So that's a problem, right? So we have two allocations. We want to do two allocations, but they have different lifetimes. So does it mean I have to supply two regions in here? Not really. There is one technique that I developed since I was working on Porth, actually, right, with linear allocator. So I said that you basically supposed to reset the linear allocator completely to 0, basically wiping out everything. But this is not true. One of the things you can do, is essentially save the current state of the allocator, right? So you can say essentially, and that kind of breaks everything, doesn't it? God damn. Right, one of the things you can do something like this, and then allocate this stuff in here. So you remembering what was the previous size in here, right? So you allocate this thing, then you remember the point in the region, then you allocate a new thing in here. And then once you're done, you are resetting size back to S. So I said that you can't deallocate specific things. You can't deallocate specific things, you can only deallocate everything at once. It's not necessarily true. You can deallocate everything up until a certain point. You can deallocate subset of it, but only things that are at the end of the allocator. Right. So we can even create a separate sort of thing for this kind of stuff to emphasize all of that. So we can define region save, and it's supposed to return the current size. And then we can define region rewind, which essentially accepts the snapshot that we take in here and it sets it back. Right, so we can kind of abstract away from internals of this entire thing and then say region save. We're saving this specific region, and this is a snapshot. And then we're rewinding this region. We rewinded this entire region like so. So that's kind of cool, right? Isn't it? We can even put something like this. Right, so we can clearly see that there is a block within which everything that allocated is going to be destroyed, but this thing is going to continue to live. So that means we can use the current region as the temporary region as well if we want to. But the problem here is that this thing has to be allocated in, yeah, what if we put null in there? What if we put null in there? That's kind of a huge problem, to be fair. So that means you can't allocate this entire thing in null. So because of that, it's kind of not going to work as I expected unless I introduce another region. Right, so, and this is the main region. And this is where I'm allocating everything that has to live long enough. So this thing has to live long enough. And the data that we generated. So matrix T generate samples. So generate samples, we provide the main region, and the amount of the samples is just samples per shape. So everything here is in main, but here it is a temporary. And we're using this rewind trick to essentially use the main region as a temporary one. So we can use the end of any region as a temporary region, right? We can just allocate something there temporarily as long as we rewind to the space back. So that's basically how we're going to do that. So we also probably need to assert that the R is not null, right? So similarly to how we do that in here, just to be sure that everything's okay. But here, to be fair, it's kind of weird. So this is an expression. So yeah, here's an interesting thing. Assignment in C is expression. So that means I can use it with a comma operator. So that's fine. That's cool. So what do we have in here? So the temporary undeclared identifier temporary. Oh yeah, okay. So I'm just like using the same region in here. There we go. So yeah, so the main thing is allocated in here, but the temporary thing is allocated in here, and it gets destroyed in here. It gets rewinded in here back. That's cool. So we need all of that because we also want to generate some verification data. Right? Generate samples also into the main. Maybe we're going to have two separate constants, right? Training samples per shape, verification samples per shape. So that's probably what we want to have. Samples. So this is the training samples per shape. And verification, maybe for the verification, we can pick something smaller, like 5. Or something like that. So let's rebuild. It's complaining because I forgot a semicolon. And we don't really use it anywhere. So what I want to do, I actually want to have 2 plots, right? So I have a single plot in here. Let's call this a training plot, and we're going to have a verification plot. How are we going to verify all of that? So at the end of the epoch, we can basically try to go ahead and compute the cost. God damn it. Yeah, we can try to compute the cost, but computing the cost requires to have 2 separate matrices for inputs and outputs. Yeah, so this is the leftovers from early designs of the library. So essentially at the beginning, I assume the training data to be 2 matrices. So the matrix of inputs and the matrix of outputs. Over time, I came to a conclusion that it's easier to actually use one single matrix, right? So you just generated the data and you pass the model that you're training and the data along, just 2 things. You don't have to pass 3. So, and overall, it's just like easier to work with, at least from the point of view of the API. Maybe it's a little bit slower, right? But I don't know. So it would be kind of nice if NN cost was like that, so I could do di append verification plot and just append NN cost for the neural network for the verification data. So we're training on the training data, and then we're verifying on the verification data. It's pretty cool, I think. So it's a training plot. Maybe I should call it T-plot because it's a very long name. So V-plot and T-plot. That's a better name. T-plot and V-plot. It would be also kind of nice to maybe render them with different colors. So let me actually like go to the compilation errors because this is going to be another compiler assisted refactoring because we changed the signature of this thing and that kind of breaks everything. Another thing I would like to have for finite differences and backprop to like completely get rid of this separation. Yeah, I think the time has come to just like completely get rid of this separation of inputs and outputs. Yeah, so we just have to pass around the neural network and the whole data, including inputs and outputs. I think that makes sense. So the API is slowly evolving, right? It's kind of difficult to immediately come up with the perfect API because you don't really know how it's going to be used. It's only after you used it for a while, you gather enough information to understand what the fuck is going on. So already, what do we have in here? So NN cost, we need to change the signature. So we're going into yet another compiler assisted refactoring where we're changing the pairs of inputs and outputs to a single thing. It checks for some stuff. Right, it checks for some stuffs. Yeah, it checks that the inputs and outputs have the same amount of rows. We don't have to do that anymore. Because it's the single matrix. They're all augmented together, right? So it doesn't matter. So here we check the columns, and this one is probably important. So essentially we can take the inputs. So this is the inputs and the outputs, and that should be the amount of columns in the matrix, right? So that's kind of important because that's how we store everything in there. So that's one thing that we want to put in here, right? So this is that. Okay, let's actually go to the compilation errors and see how it's gonna go. Yeah, so here we have this separation, but now we can just take a row and basically just take ith row, and here we're gonna slice it. Right, so this is going to be a row, but we're going to start from 0 to the size of the input size. So that's how we're slicing. That's how we're dicing. And here, we're going to start from here up until here. There we go. So the API is slightly different. Then we copy this into the inputs, and everything kind of makes sense, hopefully. Okay, so we have to provide the ith row. Go. It's not matrix, it's a row slice. We're slicing the row. What else do we have in here? So this is still cost, but we're taking the amount of column. We can just take the amount of columns of y. So it's needed because I don't really know why the fuck it's needed, to be fair. I think we could have just... Yeah, I think I used this separate variable because I was basically retyping the mathematical formula from the later documents. So, and it was called Q in there. So that's why I introduced a separate variable in here. But here it's not... Maybe I'm gonna just keep it. I'm gonna keep it, doesn't really matter that much. I hope I'm not going to introduce any errors. Okay, so in terms of backpropagation, we now accept a single thing in here. We don't split it. We don't have to check for the rows. We don't have to check for the rows at all. We have to, again, check the inputs properly. I can probably copy-paste the code from the cost. Where is the cost? Here it is. And then backprop. Backprop. Okay, and then backprop. So, and we're replacing this kind of stuff. So we're checking that the amount of columns is all right. Okay, so this is just ti. And we need to feed the inputs. So we have to do a similar thing with inputs and outputs, I think. Where is my NN cost? Where is the implement? Here it is. So we have to do a similar thing. Backprop. So yeah, so essentially this becomes input, this becomes output, and we're feeding input in here. Right, we're just feeding this entire stuff in here. All right, so then this is the output. I can just do out columns. And in here we can just do out. Ooh, and this one is interesting because out is already row, so it's already row, so we refactored this entire thing into rows, so we can get rid of I. Okay, it's simple. Okay, that's actually kind of cool. That's actually kind of cool. So what's going to be the next thing? In terms of finite differences, it's going to be similar, but we already changed NN cost to accept single t, so we can just... All right, that makes a lot of sense. Everything becomes simpler. Haha. How about that? Anything else? Okay, so this one is a little bit more... So batch ti. So what essentially we're doing in here... we're taking a bunch of sub rows. So what we need, yeah, so we need to like take a specific batch. We need to batch t. In terms of rows, it's going to be size. In terms of columns, it's going to be the columns of the original thing, right? So it's going to be this thing. Stride is going to be t stride, and elements are going to be this thing. Yeah, so that makes sense, I think. So we just like take a sub rows. Maybe there should be a similar operation to row slice, but matrix slice that gives you the slices of rows. Yeah, that would be... Yes, I think I need to put it to do in here. Introduce similar to row slice operation, but format that will give you subsequence of rows. And if we change our data representation to be column-wise, all of that is going to be inverted, actually. All of that is going to be inverted. So what else do we have in here? So we just supply t. Man, I hope I didn't fuck it up stuff. But I think that's all right. Yeah. So I think that's all right. So we take the row. Yeah. So it should be fine. And plot, and so this is a t-plot. Okay, so everything compiles, but I would like to go back to the previous demos. All right, because I'm not sure if I didn't break anything. So because one of the things we did, kind of important thing, is introduced like consolidated TI and TO. In fact, I want to look through the entire library and make sure that we don't use that combination anywhere, but we might be using that stuff still in the demos, so we need to get rid of that there. So let me quickly do that, and so it's going to be Zor. So let me see. Yeah, I was right. So that's basically what's going on. But the way we do that actually is kind of dumb. We're just generating T, and we were splitting it up into TI and TO. Because the API demanded so. But we don't have to do that anymore. We can just like generate it as we want. So yeah. Okay, so we're slowly discovering the API that we want. We're slowly discovering it. And now I can just like, and it becomes so much easier, right? So you just do backprop. And it's funny how simple backprop became. It used to like actually require so many different parameters. Yeah, but now it accepts a region for temporary allocations, the neural network, and the input data. That's it. So it allocates some memory, but it's allocated into that region, so you can then clean it up afterwards if you want to. So it's so much simpler. I really like where it's going, actually. To be fair, one of the things I would like to get rid of is probably NN-learn and tuck it behind finite differences and backprop. Right, because the way you use it, you just do backprop and it gives you the gradient, and then you apply that gradient in a separate step with this function. But what if we just like tuck it behind the backprop, because that's what we want to do anyway, right? So yeah, just like update it, and so that way you never have to even think about the gradient ever. It's just like, yeah, it's automatically updated. All right, so let me see. Okay, so I just want to see that this demo is not broken. Is it not broken? Yeah, it's fine. It's totally fine. Okay, so let's go to Ada. So demos also act like sort of tests, right? So I update something and make sure everything works, still works, by running the demos. Maybe I need to introduce like more formal tests, right? So then I have to do that, but I don't know. So here we are just allocating some stuff, but we're directly using them. But we still have consolidated T. We can just use it. So we can use this thing as subviews to generate some data, and then we can use the original one. Yeah, so that's fine. So that means here I can just do T, and that's it. Yeah, I can. So that was easy. So let's take a look at the header. It is working. Yeah, that's cool. And now, what about NN image to NN? So, and it worked? Wait, what? Okay, so apparently image to NN doesn't require any changes. Okay, that's cool. So, another confirmation that I'm moving in the right direction. Cool. Is it broken? I don't think it's broken. I think it's working. Yeah, everything is correct. All right. Seems to be working, seems to be working. Let's commit that. I think that's important because we changed the API. So do we have here get rid of separate TI and TO in the API of nn.h. Right, I'm going to push that right into the repo. I'm going to push that right into the repo. So, okay, what do we have in here? shapes. So now we can just add the verification cost. So what I want to do, I want to introduce the layout, right? So as you know, we recently introduced the layout system into the gym. So I can do gym layout begin. So we're going to start with the layout. We need to pick the orientation of the layout. It's going to be actually vertical. So I think I'm going to stack the plots on top of each other. So the upper one is going to be the training cost and the lower one is going to be verification cost. So the rectangle within which we're going to be allocating all of that is going to be the root, the whole window. The amount of elements is going to be 2, and let's put a gap between them 10. After that, we're going to end the layout like so. So then we do gym layout slot, and we're going to actually render both of them. So T-plot and V-plot. I want to actually render them with different colors. So it would be kind of nice if they accepted like red and green. So that would have been actually kind of cool. So let me see. We can literally do that. So and then here's the red. We just pass red in here, and I think this is the only place where we need to. Yeah. So because we're like drawing a line or something. Okay. So let me go to build.sh. I'm going to be building the shape, and let's go. Okay, so it complains about some stuff. So the color, I called it CA for whatever reason, maybe just typo. And here we want a semicolon. Is it going to work? I think it's going to work. Right, so essentially it's going to like stack this thing on top of each other. Maybe let's actually do horizontal one, because that's the only things we have, and we have a wide window. Yeah, I think it would make sense to actually, not stack on top of each other, but do it like that. We can stack them on top of each other if we want to put something on the right side. Right? It's super easy to do that if we want to, of course. So there we go. So we have two things, and we can try to start. Did I generate the? Yeah, I did. Okay, this is exactly what I was talking about. Holy shit, this is so funny. Look at that shit. So your training cost went down, but your verification went up. So this is literally the definition of overfitting, right? It works absolutely beautifully on your training data, but in the real world, like something that I'd never see, it fails miserably. It actually performs worse. And this is very common theme in machine learning in general, right? Sometimes it could be actually kind of interesting. Maybe your model is learning not what you expected to learn. It's learning like different aspects of the data, right? So yeah, but on top of that, excuse me, we don't really have that many samples, to be fair. Let's introduce like 100 training samples and maybe 10 verification samples, right? Let's introduce them. Let's introduce that. So we're gonna have it's doing stuff, but it's just like wobbles around, and it would be kind of nice to, yeah, it goes up. It literally goes up. By the way, do I lag right now? I don't think I lag. I think everything's fine. So verification should be between half and square root n, assuming n is kind of big. Yeah, we're probably going to do that. Oh, look at that. We ran out of memory. We ran out of memory. And this is because what we have to do. To be fair, where do we allocate the temporary? Right, so we're using temporary thing only in here. What if we do the following thing? So region, save, and then rewind. We need to buy more RAM. Yeah, so that's the problem. And it goes up. Yeah, that's funny. Okay, so let's try to do that. Let's do verification samples divided by 2. What I want to do, I actually want to make GNU plot print the value, right? So let's actually make it print. So we have a text, and we can do the following thing. We can print the last value, right? So we have a plot, and if plot count greater than 0, only then we're going to try to do that. So we have draw text, and we can have like a buffer. Let's say it's going to be like 64 bytes or whatever. And let's assign printf into that, size of buffer, and we're going to print the last value in here. So it's going to be plot items, I think it's items plot count -1. And then we're going to print the buffer at position of Rx, Ry. The size is going to be, yeah, I think that's a good size, maybe even a little bit bigger, and the color is going to be white. Right, I want this thing to be very much visible. Verification samples, what are you talking about? Yeah, training samples. Look at that. We can now clearly see the these things. And it goes up. That's so funny, man. I love it. All right, so I suppose what we have to do, we have to give it more data, right? We have to give it more data. Okay, so let's give it more data. We're gonna have 500 samples, and let's see what we have. And it's actually getting slower. Though verification cost is also going down. So I think we need to change, okay, the size of the batches. Let's say that maybe we're gonna have the size a little bit bigger, because I think like batch size 5 is kind of like too small for this kind of thing. And amount of batches per frame, let's actually start with 1 and just see from there. They're all kind of going down, yeah. But the verification, you know, wobbling around. So this kind of demonstrates, that our library is actually rather slow, right? And we probably will need to spend some time optimizing this entire thing. Though it's just like running more batches per frame actually kind of solves the problem. What about 10? But in any case, this library is very unoptimized, and I did that intentionally, right? Because I want to just hit the limit of the performance. But so far, so good. Yeah, it's kind of interesting that it hits a certain limit and it just like wobbles around. Is it possible to multi-thread it? I don't think so. Right, maybe some smaller parts of like matrix multiplication. What if I have 20 batches per frame? Okay. That's cool. So one of the things I probably would like to do, maybe I want to try different activations functions. But it would be nice to also see how this entire thing performs. It would be also nice to see how this entire thing performs. Maybe, what if we allow the user to draw things, right? What if we literally allow the user to like create a canvas and let the user draw, and it would, in real time, we'll feed that into the neural network and it will show us the current state and stuff like that. So that would be actually kind of interesting. So, well, we need to have some sort of a canvas, I think. Let me see. So gym drawable canvas. So we supply the Olivet's canvas, right? And we supply the region, the slot within which we do that. And that specific widget would just like literally allow the user to draw, right? And it will put that stuff into this canvas that we can then feed into the neural network. Isn't that cool? I think that's kind of interesting. So let's do unused. And let's maybe draw a rectangle just to make sure that, you know, we occupy the right slot. So Rx, Ry, Rw, Rh, and this is going to be red. So then, okay, so let's actually stack the plots on top of each other. So this is going to be vertical. And then let's introduce another horizontal one. Layout begin. So this is going to be horizontal one. We're going to have two slots in there with the gap 2, and the plots are going to be you know, in a slot within the higher level layout. So this is going to be gym layout slot, like so. And then in here we're going to do gym drawable canvas. We're going to provide some sort of like let's allocate some canvas, okay? OC. Let's call this entire thing canvas. And we're going to be allocating it within the main region. Right, and we're going to be drawing like this. So this is the canvas, and this is the gym layout slot. All right, so, and we need to end the whole layout like this. So it would probably make sense to also indent, think like that. So there is a problem here, is that like I do this kind of thing quite often. Like I need a slot of the size of the whole window. So in case of like sub layouts, I can always do gym layout slot, and it just gives me sub rectangle. But how do I do the root one? It would have been kind of cool, I think, if we just had gym screen slot, like the entire screen, or maybe just gym screen. And it will just like return us that stuff, or maybe gym root, I don't know, something like that. You know what I mean? So then later we don't really have to do this kind of stuff. We can gym begin, gym root. Look how nice it looks. We start drawing, we clean the background, and then here is the layout of everything. So these are the widgets. So this is how I envisioned the gym library. So you just have some training data. Maybe I'm gonna even abstract away this particular part, and then you define what kind of widgets you want to see on the screen and where, like by defining this layout. So that was the like idea, the final idea. So I think it works out, sort of. So let's see. Okay, so this thing is unused. So, and this is the canvas, and yeah. What else do we have in here? It doesn't have to be by points. Okay, so that's cool. Now, okay, so here are the plots, and on the right we are supposed to have the canvas. So as you can see here, we have two plots. So that's how easy it is to just move some things around. Right, so they were side by side, but then I wanted to put them on the side, on top of each other, and just free some space for the canvas, and it's that easy to do that. Right. So, and I want this to be that flexible because different models may require different configuration of windows, different ways of visualizing and stuff like that, right? It has to be flexible like that. It has to be flexible like that. This is probably why Jupyter notebooks are so popular among, you know, machine learning people, because they're basically that, right? So you have different cells, and different cells have different functions. And because of that, depending on your model, you can just like visualize things slightly differently. You know what I mean? So maybe it will evolve into notebooks at some point, but I think it's cooler than notebooks. You can define layouts and stuff like that. I don't know, but you see what I mean. Yeah. Okay, so The problem here, boys and girls, the problem here is that the canvas is rectangle. So what we need to do, we need to fit a square. The canvas is a square. So we need to fit square into the rectangle. So for now, we're gonna actually assume that canvas is square. We support only square canvases. We need to fit a rectangle, a square into a rectangle. How are we going to be doing all that? maybe we can introduce something like gym rect, gym fit square, and we're going to accept the rectangle. That would have been actually kind of cool. So essentially, if R is less than width, if width is less than height, so that means it's column, right? So in terms of x, we can even return something like this. In terms of x, it's going to be the same as that. In terms of y, it's going to be basically ry plus half of this thing, but minus half of this thing. And then in terms of this stuff, it's going to be this. Yeah, so they're going to be the same thing. So we're fitting square into all of that. And for the situation, this, when the width is bigger than height, is going to be mirrored. It's going to be effectively mirrored. So we're going to put it in here, but we have to use width and height in here. And here we're going to have a height. So we're fitting a rectangle in there. So, and essentially what we're going to do gym fit square into R. So that way, it doesn't matter that we have a rectangle or anything. We're still going to have a square area that fits into that rectangle. And that's precisely what we want. So let me see if it's going to work. So some of the things could be put back into gym, and it didn't work. That's nice. God damn it. Okay. So let me see what is going on. So this one is less. So in terms of x, it has to be that. Width that makes sense. In terms of y, it's actually plus half of this thing, but we subtract half of this thing. That's right. There you go. Look at it. It's not resizable. I think we need to make it resizable. Shape. Shape, where we initialize all of that, and I'm going to put it in here. Okay. This is square. Always square. It's pretty poke, I think. Anyway, so let's actually start rendering pixels and stuff like that. I think the easiest way to do that would be to actually render them as rectangles. I think that's what we can do. So we need to have a cell width, which is basically RW divided by the width of the canvas, and IH and height. Right. So let's iterate each individual cell. It can be Y0, OC height plus Y. It can be X, it can be width, it's going to be X. So the way we're going to do that, I think we can essentially say X multiplied by CW, Y multiplied by CH, and the size of this entire thing CW, CH. And then the color is rather interesting. The color is going to be the pixel, all of that's pixel, X and Y. But I don't think it's going to compile because we expect color structure. Yeah, it's going to be, yeah, the pixel is U in 32. but ArrayLib accepts a color structure. We need to convert to each32 to color structure, but I don't think we really need to do that. Right, because the color structure actually fits into 32 bits. And it literally has the same format. What I think is we can type on this entire thing. We can take a pointer to the pixel and cast that to the pointer to the color structure and dereference it as a color structure. That way we just literally take the chunk of memory where we store the pixel and we reinterpret it as a structure, and that will fit because they literally have the same format. Right, it literally has the same format, and I think it's going to work this way. So let's actually try to recompile. And let's try to run this entire thing. And okay, so something did a fucky wacky, probably because we have to offset this entire thing by X and Y, right? So that's one important thing that we completely forgot in here, right? Because we have to fit everything into the slot. So that's very important. Let's recompile. Sus, truly it's sus. I do agree with that. And I manage it. It has to be this. Right. Getting there. We're getting there. Okay, so that's something. So you can see the grid, and this is because of the rounding. Right, this is because of the rounding of these calculations. To fix all of that, we need to put a seal on them. So this is maybe self, self, like so, and maybe self here as well. So basically rounding it up. Basically rounding it up. And here's the color. I just like it's gonna take too much space, so we just want to align it like that. Not sure if it's necessary. Probably unnecessary. So the interesting thing, we have something on the canvas, and like the question is, what the fuck is going on? Like, why do we have rectangle in here? This is because where do we allocate this thing? Where do we allocate this thing? We allocated it in the main. We allocate it in the main, and we're also using the main to generate samples. And we're using that main to temporarily store a canvas. We literally see the garbage from the intermediate canvas when we were generating samples, because we allocated it into the same region. So this gives you insight into how linear allocator works. So the fact that we can even see anything is actually kind of insightful, isn't it? I think that's actually kind of cool. I do think so. Right, so let me see. Yeah, so, and this is because it's a rectangle, because the last thing that we generate in here is a rectangle. If we swap around these things, like so, the last thing we're gonna see is a circle instead. There we go. Because that's the last garbage that is left within that region. Isn't that cool? Just by switching this thing, you see different garbage in an initialized canvas. Because that's how linear allocator works. Right. Because, yeah, so it's kind of subtle, generate. Because we just like generate a temporary thing, then we first generate circle and then rectangle. And that's what's left at the end of that linear allocator. And by swapping the order of these things, we leave different kind of garbage in that allocator. So that's actually so cool. It just like gives you insights into how this entire thing works. Right. But the thing we want to do, we want to actually initialize this entire thing. Yeah, there we go. So probably want to initialize it, and what we're going to initialize it with, we can just Olivet's fill canvas with background, background color. So that's kind of cool. And there's no garbage anymore. So, and what's interesting is that like malloc can also return you garbage, right? So it can allocate you like the amount of bytes you requested, but if you look at the bytes themselves, they may contain some garbage. And that garbage also may have an explanation like that, because the malloc can also reuse some of the slots that were like freed and stuff like that. And the thing that you allocated, like it may contain some stuff from previous allocation or something like that. That can also happen. So yeah, it's kind of cool. All right. And stack can also, like when you allocate variables on the stack and don't initialize them, they may also contain the garbage, and that garbage could be from local variables of different functions. Okay. So we want to be able to draw on this entire thing, right? We want to be able to draw. How are we going to be drawing? So the cool thing is that at any moment, we can immediately get the mouse position, right? So mouse array lib. So do we have a get mouse? Yeah, we literally have get mouse position. So we can get the mouse position. The next thing we probably want to do, we want to check that that mouse position is within our region, but it has to be a rectangle. So if I remember correctly, it's something like collide or collision. Check, yeah, okay, so there's the check collision rect, point rect. You can check whether point is colliding with a rectangle. If mouse colliding with rect, but we need to convert the gym rect to raylib rect, right? So boundary, and we can say something like rx, rw, r this thing, and basically the boundary. So if the mouse is within the boundary, and another thing, we probably want to check if is mouse button down. Yeah. If you're holding down the button, let's say mouse button left, you're holding button mouse button left down, and you are within the region, one of the things we want to do, we want to actually find out the cell within which you are, right? So we can do that by dividing by this width of the cell, right? And probably also need to floor, but not really, right? So we can do something like x, and it will automatically truncate this entire thing. This is going to be y. And then you can do Olivet's pixel, OC, x and y, and we can set foreground color here. That should be enough, actually. So while you're holding the left button, mouse button, you should be able to draw foreground color on the canvas. This is CH. Let's see. Okay, so, okay. Almost. Almost. That's actually kind of interesting. I wonder why it didn't work the way I expected it to work. But it kind of, yeah. Oh yeah, I think I need to also subtract Rx and Ry, so the offset essentially. Essentially the offset. Let me see. That was easy. What the fuck? Wait. So yeah, we have a thing to draw. So the power of immediate UI, right? If you just think in immediate terms, it just makes it super easy to create these small reusable interactive widgets, right? So maybe we also want to be able to delete those things, right? So I think I first want to check if we like collide with this thing, and then depending on where we are, on what kind of button we hold, we can essentially use different colors. If we use like a right button, we're going to use background. So that way When we hold left, we're actually drawing. When we hold right, we're deleting. So this is kind of the thing we can do. So let's actually see. Okay, so let me see. It's drawing. Delete. Right. Who needs ASIP write? I just implemented ASIP write in 10 minutes or something. I'm joking, ASIP write is actually way more than that. Excuse me. That was easier than expected. We need to, who needs Photoshop EX? And what's cool is that we can move this entire thing to a reusable library. So this could be one of the widgets that you can reuse for your model, right? So you just like playing with the model and you can just like slap this thing onto your window and you can interact if you want, right? So why not? That's actually kind of cool. So, but we need to see the activations, right? So let's actually introduce another layout in here, a vertical one. Right, so, and below the canvas, I don't even know what we can do in here. We can basically feed that image through the neural network and display a heat map. Yeah, we can try to display a heat map. So I think this is going to be interesting. So I'm going to take the input of the neural network, and I suppose canvas. Yeah, we can do. What the fuck? This thing fits too well. So we can take a canvas within which we were drawing. We can turn it into the input of the neural network, which is the row, and that's it. So that's how easy it is to fit that canvas into the, like, the pieces just click together, and the next thing you can do, you can just, like, wait, what? That's too, what? How did I accidentally created two perfect pieces that just like makes it super easy? Like you have a drawable canvas, it gets updated, then you can get it and put it into the new, just put it into the neural network, forward this entire thing, and then in Gym, I think we have we have activation heat map that we can use for the neural network after forwarding it on the next. The fuck? Why is this so perfect? It's just like they just fit perfectly. What? That's too perfect. I don't know. Something wrong is here. But man, fuck, we can't see shit in this mist, to be fair. So the activations are somewhere down there. So blue is positive and red is negative. God damn it, so this is actually kind of bad. Yo, do you see that? Do you guys see that? So there is these strips, and they appear as a mod. This is so cool. What the fuck? I don't know if it's visible, but they're just like modify as a. Yeah, because they represent the input and stuff like that. That's so cool. I think I need to have something like clean up. All right, if I press is key pressed key C for clean. We can do Olivet's fill canvas with background color. So I think it's going to be useful. I think it's going to be useful because then I can just like draw and clean everything at once. Right, so something like this and clean. That's perfect. Thank you so much. The problem here is like we can't really see. But can I only draw the the last activation layer, right? Because I know, yeah, so you can render matrix as a heat map, right? You can render matrix as a heat map instead. So that means we can take and then output, then the slot, and it also accepts max width. What is max width? I forgot. It's something to make it fit within a window or something like that. It's something to, it's basically the maximum amount of cells, because we can compute the maximum between all of the layers, so we can feed them proportionally. So I think in this case we can just say and then output and then calls. So this thing is the longest thing. Right, I think it's going to work. Okay. Oh, this is a row. But row is a matrix, so who cares, right? So it doesn't matter. Fuck that. Row is a matrix. Inheritance. Inheritance, who needs OP? Okay. That's a very interesting way of doing that. So essentially, this is how you read that. Blue is positive, red is negative or close to 0. So essentially, if left one is blue, it recognizes this thing as circle. If right one is blue, it recognizes it as a rectangle. So that's how we're supposed to read that. We can try to just put something like this in here. And as you can see, it doesn't work because we didn't train it well enough. Right? We didn't have enough samples. And to be fair, like I can't really draw a perfect circle. Maybe I could just do something that it draws a circle for me. That would be nice. Let me see. Can I random? Oh, I can use random circle and I can fit. Wait a fucking second. Okay, just a second. Wait. Is key pressed key Q. Random circle into the canvas. Okay, can I do shit? I think I can do shit like that. Manual verification. Wait a second. Oh yeah, okay, so and then I can modify them if I want to. I can generate a random circle using the same code that is we use to generate samples, and then I can modify this entire thing if I want. This is so fun. And it also changes the activations down there. So can I okay, so what if I do something like if is key pressed key W, so I want to put them nearby and just like correct. What the fuck is going on? Why is it? Why all of the pieces just fit so perfectly? Like this rarely happens with me. Like what the fuck? It's just like it's so nice. It's like you're working with a framework that was designed to just do that specifically. Like what the fuck? It's just like yeah, I just like write precisely what I want, and it's kind of. Okay, so here's a bunch of rectangles, and here's a bunch of circles, and all of that I can turn circle into a rectangle at any point as well. And then I can clean everything if I want. All right, so we can try to train this entire thing. And okay, so I'm generating a bunch of circles, and for the circles I expect the left to be blue. And for some of them, I mean, yeah. I'm already getting tired because I'm trying to speak Russian. Right, so, but for these ones, yeah, as you can, it's pretty consistently being on the right. So when I'm generating rectangle, it's more often being on the right than on the left, I think. But it depends on the verification, maybe, I don't know. Maybe I'm just like confabulating. But the verification is actually sucks. Like, look at that shit. What the fuck is this? What the fuck is this? Alright, so we need more data. We need more data. That's what we need. So we had, let's put 1,000 in here. Let's put 1,000. And let's try to recompile. Okay. Maybe this is because of, yeah, it overfits like crazy. How can we make it not overfit? Maybe if we make it a little bit more flexible. What if I just cut it in half? Let's just give it more stuff. How many layers do I have? I have only one hidden layer, so I feel like it might not be enough. Okay, so it's going down. But it's too crazy. Maybe I need to... What if we try traditional backpropagation? backprop traditional. But if we're going to be using traditional, maybe I can also do activation function that is relu. Yeah, relu, I think relu could be actually faster. And if we're going to be using relu, we're going to be a little bit slower on the learning rate because it can jam very easily into nonce, nance, not nonce, nance. All right, so let me see. Okay. Well, it's going down, but it's too big. It's like 5. At least it's going down. At least the whole thing is going down. The verification. And that's on the data that it never saw. That's very important. All right. So for the circles, blue is on the left, primarily. Sometimes it has like false positive. Well, it's very confident that this is rectangle. It is very confident, right? Because this is blue on the right side. So it's super confident. What is it actually learning though? That is kind of sus. Okay, so the verification still at least goes down. What if it learns a position? Yeah, so this is the problem with this kind of generated data. Like, we don't really know what exactly it is learning. What if it learns that in this position it's a circle, in different position it's a rectangle? It could be actually learning that. It could be learning that, like, in that part of the image it's that. Fucking... that's the problem with machine learning. Like, you never know what exactly your model is learning. Right. So I remember like stories about that training a classifier, right? And they used the data that always had like a tree in the background, and what it like learned to recognize trees instead of like an actual object that it tries to recognize. Like you can't really know, right? What exactly this motherfucker is learning, right? What if it's really learning the position? Who knows? We can try to... Yeah, we can try an interesting thing. What if we use the same position for both circle and rectangle? You know what I mean? So essentially, random circle. Can we just like generate something here? So OC. Yeah, so for both of the samples, we can actually do that right here. And we can have X, Y, W, H. So basically, each individual pair of sample are going to be allocated in the same place, so it doesn't learn position. You know what I'm talking about? Right, we're going to just like, yeah, both of them are going to be using the same boundary. That's actually kind of cool. Yeah, so that might actually solve the problem. Wait a second. So X, Y, so W and H, random circle. So we can just like copy. But we'll have to also grab the radius. So that's going to be useful for that. Олівець, ось прийшов тобі то. So, where was the random circle? Can't see. Scheiße. So, I guess that's it basically, right? Олівець. Yeah, so we can do shit like that, I think. So now it is generating stuff. We can... Where is the code that I used to print the training data? Because I want to see that now. Fuck. Remember at the beginning of the stream, like I had the thing that prints the... God damn it. All right, so let's actually implement it again. Display training data. So we're going to take this thing and for... we're going to be iterating the rows. So I'm going to take the current row. So this is the row, mat row ti. So we need the input. And the input is going to be... You just deleted it, yeah. I know. It is truly Sudge. So the is going to be width, height. So that's the thing. Output is going to be mat slice. Or not save, slice. Aha, row, fight the power. Whoa! So the size is 0. This one is shapes. This one is shapes. There we go. So what we want to do, we want to actually iterate through all of these things. 0 less than height. So this one is going to be x. This is going to be width. This is going to be x. And what we're going to do, we're going to do printf, and we can do row at input y multiplied by width plus x greater than some sort of an epsilon. In that case, we're going to be just printing that twice. Otherwise, we're going to be printing two spaces. And then at the end of each row, we're going to be printing a new line. And after that, we need to print and then print the output as a matrix. There we go. So display training data. So what I want to do now, I want to just generate some samples, mainly like 4 samples. Actually, yeah, let's actually start with 4, and then we're gonna have matrix TT, and then I'm gonna do display. It was display training set, and then we're gonna return 0 in here. So that's basically what I want to see. What else do you want? Mat. All right. Okay, that's what I'm talking about. So we're generating circle and rectangle in the same place. Why there's two? What? The fuck is this scheiße? Do we have a mistake? We don't clean up this thing. Yeah, we need to clean up. Fill OC background core. I'm really glad that we actually tested that, because that would have been disaster. Oof, truly oof. Absolutely oof. I cannot even overstate how oof that is. Yeah, so as you can see, here is the pair. So we generated circle and rectangle in the same roughly space, but they have different classes. So that way, hopefully, it will not learn about position. Hopefully. Right, so at least that's what I'm trying to eliminate in here. Right, we'll see how it's gonna go. So let's remove this stuff. And really, I want to just remove this thing because these regions are important. So let's see. Okay, verification actually goes down like crazy, though it's still... The fuck? It's going up. Okay, so here are the circles. Kind of. I think we need to let it cook a little bit more. Let it cook. Let it cook. Let it cook, let it cook. It's kind of stalled. Like I feel like in here it's just like stalling. It improved initially, but then it's stalling. Sadgi, truly Sadgi. What about sigmoids? Let's go back to sigmoid, but with traditional. So sigmoid can be trained a bit faster, at least from my experience. So let me see. Can it go? It can go below 20. Alright. Let's restart. Fuck, I can't restart. I love this. The cost goes down, but verification goes up. It's just like, yeah. Welcome to AI, motherfucker. I need to be able to restart. So if is key pressed key R. Let's just do and then rand and then -1 right? Just like reinitialize random shit. And we probably want to reset the plots. T plot is going to be count to 0. All right, and v plot. But we're gonna reinitialize all of the plots. All right. Okay, good. We want to stop this thing at the right moment. So we're not lagging. Okay, hopefully. God damn it, let's restart it. I missed the moment. I think around here is good enough. Okay. What the fuck is this? What the fuck is this? According to this neural network, it's a circle. You guys think it's a circle? We got some subs. Thank you so much, Move AX13H for Twitch Prime with the message yo, ayo. It's a clearly circle, yeah, I know. God damn it. And it's just like stalls in here. But these are rectangles. So can we just try to draw a rectangle? Okay, so it's on the left. It still thinks it's a circle, though it's never seen this kind of things before. Okay, so it still thinks it's a circle. All right, so it's already recognized it as a rectangle. That's kind of cool. It's going all over the place, but yeah. It's pretty confident this is a rectangle. Actually, circles are 45-degree rectangle. Yeah, it's kind of difficult. So maybe I should make sure that this... That's actually so cool. It's very confident that it's that. It's leaning towards a circle, right? Maybe I should have like a better visualization of activation. All right. But I can see that it's more confident being for this thing being a circle. We can try to render that somehow. So let me see. So this is the activation. We're using the same slot, and maybe I can just save this slot, gym-rect slot. Like so. I'm just reusing the slot, and then I'm going to be drawing on top of the same slot. So this is the cool thing about this framework, is that I occupy a single slot, but it doesn't mean that I cannot save it and then draw on top of the slot more. I can do that. Like, who said I cannot do that? So, and I think I can do that. I can draw a text. All right, so draw a text. Let me see. So what kind of text can we draw in there? That's a very interesting question. So it's in a GNU, not GNU, gym plot, GNU plot. My brain reads it as GNU plot, for fuck's sake. Yikes. All right, so draw text, that's what we want to have. We're going to be drawing that on top, and this is slot X. Slot slot white. The way we're gonna do that, if so we have activation and then output. Let's do row at 0 if this thing is bigger than 1. If it is bigger than 1, that means it is a circle. Otherwise, if the other way around, it's a rectangle. And we're not going to take into account when it's equal. We're not going to just draw anything. That means we don't know. All right, so we've got 100 bits from who took my name. Try using 10h or sigma motivation function. Yeah, we'll try to do that. I think we're already using sigmoid right now. Yeah, I switched back to sigmoid, by the way. So this is already okay. So it already sees this thing as a circle. Okay, so let's go. Let's go. We need more data. Okay, so this is a circle. Now, if I try to do that, is it gonna say it's a rectangle? It's not sure. Is that a win? Is that a win? Probably not. We need more data, I think. It's getting worse, actually. Circle, rectangle, circle, 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 rectangle, 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 circle. It works really bad with small rectangles. Ah. Okay, let's let it train a little bit. It's super confident that this is a circle, though verification actually goes really down. So what if we increase the amount of samples, right? So training samples. So what about the training samples? 2000. I wonder if it's gonna go too badly. What if you don't feel them? We can try completely different shapes. We can try rectangles versus triangles. That's one of the things we can try to do. So this is the circle, and bias. Yeah, I think there is a bias towards area. Maybe it's actually measuring areas. So that's the problem with this kind of thing. We don't really know what exactly it is measuring, right? So we have to spend a lot of time to make sure that it is learning precisely what you want it to learn, right? It's kind of interesting, like even from philosophical point of view, and it actually goes back to alignment. Like, how do you know this thing is actually learning the thing you want it to learn? Like, is it really learning different shapes, or is it just learning the position? Okay, we eliminated the positions, kind of, but not 100%. But maybe it's learning area? What is it learning? It's learning something, kind of. We don't really know. So that's what makes it kind of weird. So that's very interesting. We can use ReLU. Let's try to use ReLU. Maybe add a little bit more layers. So I'm trying to make the layers more narrower, right? Because I expect that the first layer, the first hidden layer, is going to split the screen into small chunks, right? And learn something about those chunks, and then it's going to conceptualize even more, like compress even more information in the next layer and the next layer, and then it's just going to speed out the shapes. At least that's what I expect. I'm not an AI person, I don't really know how exactly it works. But yeah, so batch size, can we just like make 100 batches? But it's probably gonna be too slow. And 10 batches per frame. It's just completely arbitrary, I don't know what I'm doing. But it's learning something, right? So as you can see, it kind of recognizes these things. Oh, and it's, yeah, it nanned on me. The reason it nanned on me is because we switched to ReLU, and ReLU doesn't really like very high learning rates. At least in my implementation, maybe I actually made a mistake. Okay. It is slow, but I mean, At least we're not lagging, so it's just like learning very slowly. The fuck? Okay. It thinks it's a rectangle. It didn't learn shit. Okay, so it's actually weird. Okay, it is going down. But it's still kind of high. I want it to be at least around 30. I think it's not capping at least. All right, a lot of data and yeah. Okay, let's take a look at. Okay, this is circles. This is rectangle. All right. Sometimes it's a circle. We need to let it cook a little bit more. At least verification is improving. Okay, so it's going below 40. It started to go around, like wander around a little bit. So can we make it a little bit bigger so we can see verification? I wonder if it can go below 30. Can it go below 30? Yeah, it's plateauing. As you can see, it's just like becomes a straight line, so I don't think it's learning anything. Alright, so these are, yeah, rectangle, sure buddy. Not bad. That's fun. Okay, I wonder what is it going to do. Stop learning. It's gonna. Can I just draw a rectangle and just poof? Recognizes it as a rectangle, please. You motherfucker. Yeah. Let's go back to sigmoids. In terms of learning, let's make it way faster. Maybe I'm gonna like around 5. And let's see. I feel like sigmoid performed a little bit better. This is actually very good. Can it go below 30? If it goes below 30, I'm gonna be happy. I think it can at some point, given enough time. And this is completely unaccelerated, I think. Running and then in reverse to see what things. But I already spent too much time on this stuff. Okay, so this is circle. This is rectangles. Sometimes it recognizes it as a circles, but it learns something. All right, think. So yeah. Okay, so it's going up. What if I just do something like this? Just a sec. So let's actually make it 20. So I want to learn it to a reasonable state. I want to learn it to a reasonable state where it can at least be consistent. Below 20. Can you go below 20? Ah, goddammit. Oh, it's below 20. What the fuck? Can it go even further? Wait. Okay, so below 20. Can it? Fuck. It could be also learning that, well, I mean, position, it's not related to position. It's definitely not learning about position. Okay, it's consistently rectangle. It's primarily circle, but some of the circles are rectangles. Yeah. So there is a like error in here. So it's always going to be some sort of error. Circle. Okay. This is rectangle. This is circle. It's closer. This is circle. This is rectangle. Circle, rectangle, circle, rectangle. God damn it. Can you... This is rectangle. It just like needed one additional thing. This is rectangle now. Circle, rectangle, circle, rectangle. It learned something, right? Let it cook overnight. Well, I mean, I feel like letting it cook for too long is also not a particularly good idea. Right. So, but overall, yeah, you can work in that direction, I suppose. You can work in that direction. It's kind of cool. And it also always remains a mystery. What exactly is it learning? Is it actually learning what we want it to learn, or is it learning something else? Okay, it can go below 20, but can it go below 25, maybe? That would have been kind of cool. So maybe it's going too crazy. Maybe it learns perimeter. Yeah, maybe that's what it's learning. Like, you never know. It's learning something. The cost is actually quite good. So I think the most important thing to be below 30. And below 30, we may learn something interesting. Can you do some sort of a snapshot to get the lowest cost? Yeah, so but it needs to be implemented. Circle, rectangle, circle, rectangle. Oh my god, my AI just got a vision. It can see. It can recognize the shapes. Holy fucking shit, look at that. Circle, rectangle. It actually knows what the it's just like human. Holy fucking shit. We're gonna lose all our jobs. What the fuck? So yeah, so we can classify shapes. We just generated some bullshit. We trained neural network on that bullshit, and we can classify shapes. Sometimes. Not always. But quite often. Quite often it works. So let's do a committee and yesu, because I think this is a valuable example and we developed a lot of interesting stuff in here. So let me quickly just build literally every single demo just to see how it goes with 100% success. Yeah. Okay, so yeah, we broke some stuff because we used gplot in all of the models, but we now have to specify the color. Yeah. What if you hook up the inputs and outputs to the internet? It will recognize all of the circles and rectangles in the entirety of the internet and kill us all. That's what it's going to do. All right, everything seems to be working, everything seems to be twerking, and let's do a committee. That and shape. Implement shape classifier demo. I'm gonna push that right into the repo. All right, so that was fun. So maybe we're gonna extend this thing. Maybe you can extend it. Like the code is available in the description and also for the people in the chat. It's mn.h. The demo is already there. You feel free to extend it and just see if it learns better or something like that. But we definitely need to invest a little bit more time into optimizing this entire thing because I think it's getting slower. It would be nice to use LAPACK or something like that, or BLAS. I think BLAS would be enough to just speed up the matrix multiplication and addition. But we'll see how it goes. All right, that's it for today. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you all on the next recreational programming session with Azuzin, and we're gonna do something cool again. All right, thanks everyone for watching. I love you. Mwah.